I think we are live. Hello, any future viewers. I'm Mike Science here. I'm here with Space Audits, and I've been calling you Alan. I hope that's okay.
Oh yeah, that's fine. I
Yeah,
just
and
changed it
you can
because
call
of
me
the.
Matt if you want.
Yep.
Yeah, Space Audits is the new YouTube channel that you got going on. So a little shout out for that, right?
Yep.
Okay, we were talking about pressure and containers and that whole thing, right?
Yeah.
I think anyone who's going to watch either of our channels probably knows most of the background, right?
Yeah.
You
This
want to
should.
summarize? You want to summarize your background on that, or like what are we talking about?
Yeah. So the official narrative of how the atmosphere works is that it just fades into a gradient of nothing, right?
That's
Essentially.
fair. Yeah, I mean we start with pressure
And
down here, and it fades to nothing up at the top.
yep. But you do acknowledge that a container would be required, but you think the container would be a force field of gravity.
Well, I would say that you could call that a container, right? I mean, you need to be words are fuzzy, right? What do you mean when you say container?
Okay, so when I say container, I mean nothing's passing through it, nothing's getting out. So I guess that would differ from your version of it because the atmosphere does let some air molecules or whatever escape, right? So
right,
I
so
guess that
it's
would be kind of
mostly
different.
contained
Sure. Okay. Yeah.
by yeah. So it's mostly
yes.
my position is it's mostly contained, and it's contained by virtue of gravity. Yeah.
Okay. Yeah, and then so my position would be that if a larger low pressure system existed next to our pressure system, it wouldn't just stop at nothing. It would just go all the way down to the surface of the Earth. And I think that in order to stop that, whatever, or to even have a gradient to begin with, because we were talking about how that's formed from the buoyancy and stuff like that, right? So in order for that to take place, it has to press against something. Like there has to be pressure, right? So there has to be a physical container for it to press off of because nothing. Have you ever seen anything press off gravity? Like I mean, so
that's a weird thing to say. Things don't press off gravity.
Well, then how do we have atmospheric pressure? What's it pressing off of?
That's a good question. And I guess we could start there.
Okay.
Why don't we start there? What is gas pressure? What is atmospheric pressure? What does that even mean? What does it mean to you?
So what it means to me is when there's a container with a gas in it, it will, there's the pressure will be concentrated at the lower part of it, and there will be a fading gradient up to the end of the container, right? So like when you have like a propane tank that's very concentrated at the bottom, it's like liquidy, the propane, and as it gets closer to the top of the tank, it's the more gaseous, faded gradient, quote unquote. And but obviously the propane tank is a container in and of itself, and I think you'll find as we continue to discuss this that every single example that you give is going to require a physical container to demonstrate what your position.
Okay. All right. Let's back up and dig in a little bit more on what is pressure. I would start with pressure is force. Pressure is force over a unit area. Does that mean anything?
Yeah. So if you're filling up a container, the gas is like pressing up against the container as it fills up more and more. It's creating that pushing force, right? Or as you were saying.
Yeah. So if you pump gas into a container, you increase the amount of force that's pressing on the sides of that container.
Correct.
And when we say pressure, we measure it in force per unit area. So that indicates that the amount of force is distributed evenly within the volume of space so that it's pressing against the surfaces.
Makes sense so far. I'm with you.
Okay. So the amount of pressure would be measured in units of force per unit area. So PSI, for example, pounds per square inch. And so that's what pressure is. And when we talk about pressure from a gas in particular, right, like the air, what's causing that force? Why does gas push on containers?
What do you mean? Because it's contained in
Well,
like
go further. I mean, don't stop at because there's a container. Tell me why. Why does air push on a container?
Because it's trying to, isn't it trying to Well, are we talking about like if you keep trying to fill air into it, or just air that's sitting in it like stagnant, like it's like filled almost to the top or something like that?
I don't know. I mean, I guess I'm asking, what does it mean to you? I can tell you what it means to me. I tried to explain to you in, I think it was a YouTube comment. I was explaining.
Oh, the fence thing?
Yeah. Air is gas. Gas is made of molecules.
Right.
Is that a controversial thing to say?
No, I'm with you.
Okay. And molecules in a gas, they're very free to bounce around. They're not bound to their neighbors.
Right. Okay.
And that's what defines what a gas is. A gas is where the molecules are free to move around. And so if the molecules are moving around, they will bang into their container.
Right.
That's pressure. That's the force. The force that the container feels is when a molecule bonks into it. It gives it a little push. And the molecule bounces off.
Yeah. I thought you were talking about like something else. Yeah, what you're saying makes sense. I got you. I'm with that.
Okay, so that's all pressure.
When you were saying that, like, just okay. Yeah. Gotcha.
Yeah.
We're on the same page so far.
Good. Yeah. I just want to get to stress that it isn't a magical thing, and it isn't something that we're just indoctrinated with or we just believe because of reasons. We understand that when a ball hits a surface, it pushes on the surface as it bounces off, and that's not
what's in dispute, though.
Right. It shouldn't be in dispute. So we're just laying some good groundwork here.
Okay.
And so why is the container needed? Why can't I do without the container?
Okay, well, as you mentioned earlier, pressure is the little gas molecules pressing up against the container. So that.
Right. So if I don't have a container, do I still have pressure?
Not in the sense that you have a pressurized container of something, like no.
Right here in front of me.
Yeah, because there's a base. Yeah, because bro, you're in a container. You're in a further container, bro. So
there is pressure right there. Well, yes, sometimes I have to clarify because sometimes people say, I've actually heard people say, you can't have pressure without the container because we just described pressure as the force the gas exerts on the container. Haha, got you. Right? I'm just making sure you're not saying that.
What I'm saying is, what you're saying is that pressure is pressing off of a container. And what I'm saying is the container is definitely an essential component to pressure if it's pressing off of the container.
I want to know why. And I think we're right there on a really good suggestion of why.
Well, why do you think it's not? Because it seems pretty self-evident to me. Like, I'm not sure how to.
Well, self-evident doesn't apply for me. I'm going to need something better than self-evident. Self-evident doesn't work, right?
Fair enough. But okay, well, let me ask you this. Earlier when we were talking about a demonstration without a container, what demonstrations do you have? Because if you can demonstrate it,
I haven't given you one yet.
Okay.
I have
Because that
some. I
okay.
have some. But
we'll drop the gravy, bro.
Why do we need that? I'd like to get into a different kind of thinking where
okay, so are you familiar with rhetoric and
the
dialectic?
role of the container. If you understand why the container, I'm sorry, you go ahead.
Are you familiar with rhetoric and dialectic?
No.
Interesting. So you should probably learn about that. So some people don't respond to facts and stuff like that. Other people do. Some people respond to like social shame and critique and like humor kind of thing of a presentation. So you can sway opinions that way. So if you're going to make the argument that it's possible to have it without a container, like I do respond well to like facts and stuff like that. I'm not strictly. I think it would be dialectic that responds to not factual things as the rhetoric. But yeah, so if you have something that could show me that, then I would be more able to accept what you're saying, because without a demonstration, I mean, flat earthers have been talking about this for years, and I've literally never seen anyone demonstrate what you're talking about, other than when they say, well, a mountain pressure gradient, blah, blah, blah. But that's not acknowledging that we think that we're in a container already. You know what I mean? So it's kind of like a non sequitur point for you guys to make. So if you have a better demonstration of it, like, please tell me, because that would help me be able to accept what you're talking about to begin with.
All right, I can think of a couple, and I would bet that you've seen at least one of them. And I respect what you're saying. I definitely do. And that's really what I want to highlight. That's the important thing about the conversation, I think, which is that you think of it in a different way than I do.
Yeah.
We're going at this from different angles. You're coming at it from all these examples have containers. Proof, right? There's a container there. Any examples I'm going to show you, you're going to point to the container and say, see, there's a container.
Yeah.
And I keep trying to say, that's not how science works.
Well, even if it's not how it works, it's still like if
it's moving. It's emotionally moving. It's how you think. It's how you're going to process this, right?
True. Yeah.
And so maybe the fault is on me for keep trying to get down into the science when you're actually going to hit a wall as soon as I show a container.
Yeah,
you're going to be like, there's a container.
After this video, I'm going to link you some dialectic rhetoric stuff to help further explain that, because I think that would actually help you in your cause in that, because because on some of the stuff in our correspondence, when we're like setting up the baseline for what we agree on and stuff, like I'm like ready to get further into the conversation, because I'm just like, come on, man, let's get to it. So I kind of like breeze over things and stuff like that, and then we have to go back and backtrack to correct what I fucked up, and I do apologize for that. And I wasn't trying to, you weren't even accusing me of it, but I wasn't trying to backtrack on you. I was just like, okay, now we're talking about it. Now we can get going, So.
Yeah, and I get it. And I think the best way to describe, like for our audience, the way the conversation's been going before we brought it to YouTube here, I keep trying to drill down into the nitty gritty, itty bitty tiny, and you keep trying to think of the big picture.
Yeah.
And
I would say that's pretty. That's really accurate. Yeah.
And because of that, we just keep butting heads, because I'll say, yeah, but down here, this is what's going on down here. And then you'll say, yeah, but it's out here. This is what's going on out here. And I would literally say, stop thinking about that. Just do this with me. And you do that with me. And then as soon as I'm done, I'm going to say, see, I proved it. And then you go, yeah, but the big picture. And you're right back.
Because you'll prove like a small aspect of something, or you'll prove something towards the baseline of what we're talking about before we get to the fuller thing. And shit, there was something I wanted to add to that, but it literally just escaped me. So go ahead and continue.
Well, okay. Well, think about it. While you're thinking about it, let me change tack then.
Mm-hmm.
One of the things that's a real blocker for you is that all these demos and explanations that we talked about all have a container. What if I gave you an example that has no visible container.
Well, that would be extremely helpful to giving me something to actually dissect and look into,
Okay.
other than the fact of operating on, what I already know.
The one we usually see people bring up is the fusion reactors. Have you seen those videos and photos before?
No, or I've heard of them and stuff. I've kind of looked into them, but go on.
Okay. I forgot the proper name of it, but it's a magnetically constricted fusion reactor. The idea is that they take energetic plasma, which is ionized gas, and they squeeze it using a magnetic field, trying to get it so dense and so hot that it will start nuclear fusion. And they've done it. You can do fusion that way.
Okay. Which one's the one that they're working on and can't do? Is that fission or fusion? Which one? Because there's two of them, isn't there? Which one's the one that's theoretical? Which one was that?
Neither one is theoretical at this point. We have both.
Oh, no shit.
But what we can't do is use the fusion for anything useful. They can get fusion to happen. Well, that's an exaggeration too. You can't make energy out of it, is the problem. You can get it squeezed so hard that it starts fusion. And sure enough, the reactions happen and you get the energy coming out. The problem is that it takes so much energy to squeeze that plasma that you're burning more energy than you're getting. And so that's the big push that is going on in that field right now, is trying to get it cheaper and more efficient so that we're breaking even and making energy out of it.
Right. What did you say? What did you say plasma was? Ionized gas?
Ionized gas, yeah.
What does that mean that it's ionized?
Okay.
Was it like charged or?
Yeah, charged.
So electrically charged or?
Yeah, electrically, yeah.
Okay.
And the way it works, I mean, we talked earlier about a gas molecule bouncing around is what defines gas, right? Is that the molecules aren't really bound to each other. They just kind of move freely. In a plasma, the electron that is normally bound to the nucleus isn't bound either. The thing is so hot that the electron has been stripped away and is freely bouncing. So you got the electron going this way and the neutrons and protons going the other way. And they're just like all bouncing all around.
So plasma would be outside of the three normal states of matter, right? Solid, liquid, gas. So this is a new thing, right?
It's usually called the fourth state of matter. Yeah. Right.
So that's the first time I've heard anyone give an example of a container without a barrier, or, physical barrier. But to that, I would say that, this is an entirely different state of matter that's going on, that's being changed and contained by something that's not what's claimed by the Earth's atmosphere and gravity, right? So I don't want to hit you with so I don't want to hit you with a non sequitur, but like, is that would it be fair of me? Would you think it would be fair of me to say that that's not really analogous to what we're talking about with the Earth's atmosphere and regular gas and all that?
I don't know. I mean, I think it's semi-fair. I think it's what I expect you to say.
Because your example does require. Yeah, well, your example does I acknowledge that. That's cool. Like, I didn't know that. That's really cool. But your example requires very specific conditions that isn't what's being claimed by.
Right.
So
the differences. Let's highlight the differences. We won't be dismissive about it, but we should look at, is it a fair analogy?
Yeah.
In the reactor, it is magnetism, is electromagnetic force, is the force being applied. Whereas in the atmosphere, the claim is that it is gravity being applied. Although, let me point out that for the people at home, they don't know, but as we've been talking, I continually have said, I don't want to get into what gravity is because I don't think it's necessary. We don't have to talk about what causes gravity at all. Only that we observe that it happens.
Fair enough, because we both agree there's a downward bias. Like, would that be Like we can just
yeah, I mean,
yeah. So yeah, for those keeping score at home, we're not disputing that things don't fall when you drop them and stuff like that.
yeah, stuff
We're in
falls.
agreement with that. He thinks it's due to a different reason than we do, and that's all there is to it. But
Right. And I'm just saying for this discussion, the discussion about pressure and containers, it's irrelevant. It doesn't matter what causes it, so long as it does happen. And I'll go one step further to remind you that your hypothesis for what causes it, or your theory maybe for what causes it, is that it's the electrostatic force.
I'm a big fan of the electrostatic gradient.
So when you say to me that the magnetic constriction is not the same force, I'm going to say to you, isn't it though? Didn't you say that gravity was caused by the electromagnetic force?
When you say, yeah, let's see here. I think you're right. Give me a second.
So, I mean, I say it isn't, but you don't get to object.
Okay. Run that by me one more time. What was it again?
Okay. Your theory of what causes gravity is that it's based on the electromagnetic force.
Static electric, not
static electricity. Yeah. Electrostatic.
Okay. Yeah.
And the fusion reactors are using the electromagnetic force to constrict their plasmas. So doesn't that make them the same force?
Yes, but it's constricting a plasma though, right? So it's, so you have to charge it. So you have to charge it. You have to create an additional condition for it to simulate like a container to push off of, right? So So yeah.
Right. Okay. So the electromagnetic containment wouldn't work unless it was a charged ionized gas somehow. And so once you ionize the gas, then it works. So it's different in that way, because we're definitely saying that this atmosphere that I'm breathing in now is not ionized, right?
Mm-hmm.
So the irony here.
Oh, dude, I see it. That is, yeah, you're right.
The irony is that you just argued yourself out of the electrostatic theory of gravity.
Yeah. No, I see it. True. I saw it. Like, yeah, I saw where you were going like a couple of seconds before it happened. Yeah, true.
Which wasn't our goal or the conversation, but I guess next time.
No, that's hold on. I'm going to write that down real quick, because that's actually super important. So thank you for pointing that out, man. Yeah. What was let's see.
Yeah.
Okay. So fusion reactor proves, what's it called? Electrostatic. Yeah, dude, I'll look further into that and get back to you on that. I 100% see what you're saying. You're absolutely right.
But that's not our actual topic.
Touche.
But it's an interesting thing to learn. And so, getting back to our actual topic, do you have a good argument? In a way, but now you're in a place where you're going to have to say that electromagnetism works on ions and can do what we're talking about. You can create pressure surrounded by vacuum using electromagnetism and ions. You agree to that. And then you have to say, but other forces can't do that. Only electromagnetism can do that.
1 second.
And I'm going to come back to why. Why do forces are forces? If you push on something, you push on it.
Okay, so in the regular example of Earth's atmosphere, right, with regular gravity from your perspective, I'm sorry, go ahead.
Yeah, I was going to say whatever it is. I don't even want to say.
Yeah. Whatever it is, just what's pushing? Like, do you have something that you can push against gravity right now? Like, what does that even look like? Because in the fusion reactor example, I mean, they got a whole fusion reactor situation
against gravity, right? Push. push. It's there, and it pushes against me constantly. I can't stop it. It's just always there. Nothing that I've ever tried has really been able to get rid of that.
It's not really what I meant by you picking something up. I meant in the context of the gas molecules bouncing off of gravity, right, to create the pressure.
Well, they don't bounce off of gravity. They get they get pulled down by gravity like that.
Well, no, but you said that it forms the container in which it would bounce off of to simulate the contaner, right?
Oh, you don't bounce off
that's
of it. Well,
that's what I. Well,
Here, let me
so
bounce,
you know, hold on.
Let me bounce my octopus off gravity for you, right? Okay, it's gonna go up. It's gonna hit something and bounce back down. Watch this.
Nah, that's not, bro.
Why is that not a bounce?
The thing you're bouncing is more dense than that medium that it's in, so it's going to go down regardless, right?
Whatever causes it, we're not arguing about what the cause is, but you see, this thing can only go that high.
Okay,
can't go any higher than that. Because
let me rephrase my statement then. Can you throw something that's lighter than air that bounces off gravity? Because that's what we're talking about, gas, right? So what can you throw that bounces off gravity? Or
you're now talking about buoyancy, right?
Right. Which requires.
Are we going to have to get into buoyancy?
Yeah, we're going to have to get through the whole thing, brother. We're getting to the bottom of this shit tonight. like we're solving the whole thing, dog.
All right. Well, buoyancy is a long, separate conversation. Buoyancy requires gravity. Buoyancy does not work unless you have something pulling down.
Okay. And also a container for the medium to be pressed against so that it can be displaced, right?
No, the container is absolutely not required.
How's that?
We just showed that any force that acts on your fluid medium can compress the fluid medium, right? I mean, you don't need a container. You can use any force. Any force that works, right? I mean, you need a force that works. And the obvious one is a container. You get a container, and you crush it.
Hold on a second. I'm picturing something different.
The medium.
So, hold on a second. Well, what I'm talking about here is take the density tower, or what was it called? The buoyancy tower. Okay, so take that for example, right? The different liquids inside of it. Okay. If that wasn't in a container, like for example, say you had it like an infinitely long table or something, right? And you just poured a gallon of whatever liquid, and then you poured another gallon on top of that gallon. There's not going to be any separation gradients or anything. Like they're just going to keep, like they're not going to
spread out.
Yeah, they're not going to do right. They're not going to do the thing that you're talking about.
They would spread out and lay flat on the table.
Without a container, yeah.
Well, it wouldn't do what table. You just talked about an infinite table, right?
Okay.
So I'm going to pour an infinite amount of liquid.
Oh no, we're not doing an infinite. We're doing
Well, hold on. You started it.
Okay. Well, then regular size table.
Why are you cutting me off?
I don't mean to cut you off, but I see where you're going with it. But it's not relevant to what I'm trying to talk about. Because
I know what you're trying to say.
Yeah,
I think you're trying to say that without the size of the container, the liquid's going to spill and just go flat.
Yeah, you're not going to get the gradient, right? And I think that's like a fractal of how the whole gradient system works. I think you can get insights into that are just how things work, right? Because dude, a fucking apple, they say an apple fell on dude's head and he figured out that gravity exists. So if you look at a bunch of density containers, why could you think that it's possible that everything requires a container to have density and pressure and stuff?
You absolutely could think that. You could think that. But then I'm going to ask you to experiment with it and prove it.
Okay.
And what I'm going to do is I'm going to say, show me the role of the container in this situation. What force is the container imparting, and how does that force change the dynamics?
The container's
Right.
molecular bond is holding what it's containing, and that is creating pressure for the liquid and or gas to press against to
I
to
agree.
settle in and create a gradient. And then to take it furthermore, if there wasn't a container, like you couldn't even like, dude, see, this is where it gets crazy, bro. Because if how could you even man, and we're back to
But
square
then
one. Shit. Dude, yeah,
no,
sorry.
and we are back to square one.
Mhm.
On a table, if you put water on the table, it goes flat because there's some downward force, right? Because the downward force is pushing that water down. It wants to go down. It goes down as low as it can go.
It's not just that though. It's more dense than the medium that it's being poured out of, right? Yeah, because for sure.
Yes, but without the force, density doesn't do anything. You need the force and the density.
The force is that there's a container.
The container does not impart a downward force. The container
Dude,
does not impart a downward force.
No, but it creates the necessary requirement for like air to be here for something to be heavier than air.
That's just an intuitive leap. You haven't proved that yet. You're just saying it. Right?
Okay.
Show me why is it necessary. Let's start with the liquid again. Liquid in a glass. If you pour it, it goes down. First of all, it goes down. Why does it go down? It's denser than the medium of air. Yes. And there's a force acting. That force separates things. It pushes on things so that denser things go down.
If there was a force pushing on something and there wasn't a container, it would just push it out of whatever it is, right?
Well,
and then also
pushing it down. It would keep pushing it down until
no, but then when it hit the earth, it would just push it out. Like it wouldn't be able to contain it. Like that's
Absolutely.
why.
So it would
that's
spread
why
out. It would spread out. Right? It would go down until it hit a surface, and then right.
Well, no, no, because if there wasn't a container, the thing that would be going down would just be a low pressure, system would just replace the whole thing if it was gas, right?
I don't know what you're talking about there. We're talking about liquids right now.
Oh, sorry.
You were pouring a liquid into a container, and we're talking about what is the role of the container. And I said the container is needed to keep it, because if you don't have the container, the water will try to go as low as it can.
No, my bad. When we were talking about I think it was the atmosphere, whatever we were just saying. So I switched to gas. I thought we were
right. We'll get back to gas.
Okay. Yeah. So the function of the container is for it to hold the
spreading out, right? Keep it from spreading.
Yeah. To give the liquid form, because liquids take the form of their container, right? If there's no container, then there's no form.
Well, why did they take the form of the container? Again, don't say incantations like they're magical. Tell me why.
Their molecular bond isn't strong enough to form their own thing, right?
Cool. Yeah. Liquids. There is a molecular bond there, but the molecules can slide against each other, and so they can basically take any shape. So if you push down on it, it wants to go down. It's going to go down as it can. So on a flat table, that means spread out and get down on the table, right? Lay down on the floor, so to speak, right?
Right.
And so we need that container to keep it from spreading outward, right?
Yep, agree.
But we don't need a container. This is something I asked you in the email. We don't need any container on the top surface. That stays just fine without a container.
Well, yeah, because we're talking about liquids still, right?
Yeah, we're talking about liquids.
Well, did you see what I said to that?
Density was basically what I got.
Well, no, was it your assertion that the liquid would somehow be wanting to float up against?
Well, if you didn't have a downward force acting on that liquid, it would just go every which way, and then you would need to contain the top.
One sec.
But yeah, okay. Hello, a lot of people have joined in, a lot of comments while we're in the 1 sec mode. Yeah, we have covered a lot of those things at some point. So this is a very different conversation than I think usually you get in this space. First of all, because we're not going to yell at each other. I think we're actually trying to understand each other. I think. Which
so yeah, I guess that's true. In your guys' paradigm, if there was no gravity, everything would just be floating around. So,
right,
fair enough to claim I don't have a response for that at the moment. But
okay, I mean, it's not just my paradigm.
But yeah, because
you're too. If in your world, if there's not something pushing it down, it goes up or goes every which way, right? Something's got to push it down, whether it's electrostatic or just density or whatever. Something's got to push it down.
Yeah, fair enough. I didn't say that correctly. So,
so what that brings me to is that the surface of the water does not need a container because there is a force field present that is pulling it that way. It's pulling it down.
Okay,
there's no force field pulling it in.
Okay.
So we'll need a container to provide that.
Your force field, though, okay, so like it's containing the liquid, right? But it doesn't contain a helium balloon.
Well,
okay, the consistency. So buoyancy overcomes your gravity, downward gravity, right? Because it was not strong enough to overcome buoyancy. That's why things would float if they're less dense than the medium they're in, right? It completely annihilates going to the center of the Earth. Or I'm sorry, I didn't mean to bring in what. It completely overrides the downward bias, right?
So how it is a side effect. Buoyancy is a side effect of gravity. Once you understand gravity and just basic Newtonian dynamics, buoyancy is the side effect. It's unavoidable. So we can get there, but I'd rather avoid that conversation. And that's where it's going to go, right? It's going to go to why does he float? Because of gravity.
Oh yeah, dude. Yeah, see, that's where, dude. Yeah, gravity, dude.
It's all gravity.
It's all gravity, dude.
It's all gravity. And so maybe I was hoping maybe we could just sort of table the buoyancy thing for tonight, or at least for now, and try to talk about why the container is needed. Right.
Well,
let's leave helium out of it. And just talk about the water and the air and the glass container for now.
Well, I think I've illustrated that it gives things that don't have molecular bonds strong enough to make their own forms. It gives them a shape. It gives them the ability to assume a shape and have form.
Yeah, and I added that the reason we don't need a container lid is because there's a force field pulling downward. And that means the reason we do need container sides is because there's no force field pushing sideways. The force field pushes down.
Now let me ask you this. There's no force pulling sideways, right? But isn't the sun pulling us sideways?
Long answer, short answer, no.
How's that? Isn't the universe flat or the solar system flat?
We're on a disk. The solar system is on a disk. Slightly longer answer is you can't feel gravity.
So, see, this is where it gets really confusing because
you can't feel gravity if
you can't feel it
if you're in free fall. Okay. When you're in free fall, you've seen this on the Vomit Comet or whatever, right? It just looks like somebody shut off gravity. We're in free fall around the sun, so we're not going to notice that. Also, it's
okay.
It's teeny bitty.
Hold on.
But even if it wasn't teeny bitty,
okay, so in order to be in free fall, there'd have to be an up and down, yes?
I would almost agree to that. you'd
I
have
mean,
to
see, this is where it gets tricky because there's no up and down in space, right?
I don't know. I mean, you can define up to be away from the vector of gravity, I suppose, right? That's what we do here on Earth.
Well, isn't the vector of gravity every direction?
Yeah, kind of. If you zoom out to the whole Earth, right? At any given spot, gravity pulls you down, right?
Yeah.
And so we say that's down and that's up.
But never to the side, though, right? Never on a tilt, right? It's always in one direction, right? Now they've told you that the cause of that is because it's going to the center, which I know we're not getting into, but like I'm with you that there's a downward thing, but it's always going down, right? And we know that there's a down, right? Because you're referencing free fall. So there's an up and there's a down. There's no relative up, like that's doesn't make any sense.
I don't know. I mean, it's an orbit, right? An orbit goes round and round.
But we're going sideways. Like we're being pulled to
any which way, right? You can go round and round sideways. You can go round and round up and down. I mean, however you imagine it.
Mm.
Like you said, there's really no up and down in space. It's all arbitrary.
Mm.
But yeah, I think that's kind of off the topic. So stick a pin in it. We'll come back to explaining why you can't feel gravity and free fall and what an orbit is like and what an orbit feels like. We'll come back to that some other day. For now, I had said that you don't have any force field to the side, but you do have a force field pointing down. Mm-hmm. And that's why we need that container to hold the liquid. And I wonder, will you go with me on that and say, yeah, that's actually correct, I agree, or no?
100% agree. Okay. So could I get you open to the possibility that the Earth has giant walls that form a container around it? Would that be more? Would that be more your style?
I think that's what we should then discover. What we just discovered is that the flat Earth doesn't need a dome. The flat Earth needs a jar.
Yeah, sure, okay.
It doesn't need a lid.
Because I honestly, dude, I'll probably catch some flack, but I can agree with that, dude.
But it does need walls. The flat Earth needs walls.
It does need walls.
Tall walls that are 100 miles tall to hold in the air.
Sure.
Or maybe it could be a dome, I guess.
I almost believe it anyway because I just believe it just connects at the top like a dome. So it's not too far of a stretch to do that. But I totally understand what you're getting at now, and this has actually been really helpful because it's actually there's this guy I've been watching. You can check out his. I'll link you his channel real quick.
Yeah, slap it in.
He's super into he's super into like debating and logic fallacies and stuff like that, and just like logical analysis of things. And here's his channel. I think that video is the link to a moon landing one, but he's been doing a lot of flat Earth coverage and coverage of the debates of flat Earth, or that flat Earthers do with other, globe enthusiasts and stuff. And anyway, I thought some of the stuff he said was
so Alan's vouching for it. So watch it your own.
Oh yeah. Yeah, so I'll just give you a heads up. He's not like a conspiracy guy or anything, and he doesn't make any claims about the globe or flat Earth that I've seen yet. But he just He just looks at what other people are saying. And he's like, "This is a logic fallacy. Here's why." Blah blah blah. And I just find that really interesting. And I forget where I was going with it. I got super sidetracked. What were we just talking about? Can you help me out?
About whether you needed a jar or a dome on flat Earth.
Yeah, shit.
You need a jar, but if you're going to build a jar, you're probably going to put a lid on and make a dome.
Oh,
right?
Yeah. So what he was saying, sorry, thank you. Okay, so the reason I brought him up was because he's made a lot of analysis that some of the arguments that we make and some of the arguments that you guys make, like it doesn't prove anything either way. And I think arguing over, like using the rhetoric, I think you're right, man. I don't think it would prove anything either way in terms of shape, obviously. And I think you did illustrate that you don't need a lid at the very least, which I'll concede that because that's that's in the examples that are given. So
okay,
that resonates well with me. And
awesome.
okay,
I'm gonna call that a win. That's awesome. That's awesome, Alan. So yeah, you don't need a lid. You do need sides, though.
Sure.
Because on the flat Earth, you don't have any sideways force.
Well, either do you, because gravity doesn't pull anything sideways.
Zoom out.
On right? What?
Zoom out on you got water in a jar on a table. Zoom out. Zoom way out. Can you think of a shape that could contain something on all sides?
Bro, you know my position on that. Like, yeah, obviously the globe.
A globe would not need a lid. But flat Earth does. Well, that flat Earth doesn't need a lid, it needs sides, right? Flat Earth doesn't need sides. Globes
flat Earth doesn't need sides.
Flat Earth needs the container to keep the air from getting off on from the ice wall or whatever.
But that only works though if the Earth is actually a globe and if gravity is attracted by the center of mass that though.
Whatever gravity is,
because if it's not, then
we're center. As long as it pulls things to a sphere, we don't need a dome.
Yeah, fair enough. So because fair enough. Because if you guys, totally.
That's my whole thing. Is not not that it proves there's no dome or it proves that there's a globe. It's just that when you hear people say this, and you hear them say it all the time, that the atmosphere proves that it's not a globe. No,
yeah, dude, that's what logic fallacy guy was talking about, and that's really resonated with me recently, and I'm trying to do like a revamp of going through this stuff because I think a lot of these arguments are fallacious to just get us fighting over nonsense and shit. Like imagine think about how many people have been arguing in comments section, and I'm guilty of this too. I'm not trying to say I'm above it. I've been in the comments slaying kids about containers, so it's all good. But so just think about we're fighting over that, and neither one is correct, right? Or I mean, potentially neither one could be correct.
Right. The logical question is not which one is it. The logical question is, are those consistent with themselves? Are they self-consistent, and are they consistent with observations of reality? That's all that matters. And so when someone says, the second law of thermodynamics proves that we have to live in a container, no, it does not. That is way, way wrong, and you need to tell them that.
Well, the only thing I could see to that would be is a lot of people don't think that, and myself included, that the low pressure system of space would stop at space and then fade into a gradient. Most of us think that it would just go down to the surface of the Earth. Like, why would it ever stop? Like you say,
Right? Yeah, and we could get into that next.
And that's another reason where most flat earthers, or pretty much all of them, I guess, are about that container lifestyle, because it just seems, it just seems like it is necessary,
Okay,
but I can see what you're getting at, and I'll think about it and stuff. You're making more sense than I originally was looking at, in the emails. I was like, why doesn't he get it? I just kept.
Yeah, no, I think I get it. I do get it. And hopefully you get it as well. And yeah, where we landed is, if you believe in your heart that the Earth is flat, then there must be a container. Or there's two options: either it's a container or it's infinite. If it's truly infinite,
then
I guess you don't need a container, right?
Yeah, see, I'm not an infinite person myself, but there are some infinite lads out there. So shout out to the infinite plane guys.
Okay. Infinite plane peeps. And on the flip side, though, if you entertain for a moment, what if it were a globe? You don't need a container on a globe because you've got the force that pulls the things towards the center.
Yeah.
That's it.
Well, yeah, we all generally, understand that part of it, but where we've differed is just well, a lot of adjacent stuff that isn't related to this specific topic has just completely destroyed the notion that what's presented about the quote unquote globe is legitimate, So once that's been
claim.
Well, I think we've been over some images and stuff that are some of the biggest evidences, and we've proved that those you can't really verify if those are legitimate or not.
Okay, logical fallacy.
Okay.
One's inability to prove that an image is real does not prove that the image is fake. Right?
True, but if you're going to say it's real, then the burden of proof is on you, and you can't prove it. So
let's not do the reversal of burden of proof fallacy. That's another fallacy, right?
Well, hold on a sec.
You're making a positive claim. I'm making a positive claim. I can present evidence for my claim. The photograph is not my evidence, is not my claim, right? I'm going to use things like the solar thing that we did, for example, observations that normal people.
Let me ask you something. Have you heard that Einstein quote where he says something to the effect of, "I've come to the conclusion that no optical experiment can prove the motion of the Earth"? Have you heard that?
Yeah, sure.
So he probably knew about Eratosthenes and shadows and sticks and stuff, right?
Mm-hmm, mm-hmm.
So
that's not what he was talking about.
So what was he talking about then?
Because he was talking about relativity.
So he's saying that his own theory can't be proven?
No, that's not what he's saying. He's saying that is his theory. He was describing his theory. His theory says that you can't look at other objects to say how fast you are moving.
Oh, okay, interesting. So we're just out of context on that, I guess. Yeah. Okay, fair enough.
And that's Einstein's just special. That's just special relativity, right? Either, when you're driving in a car and you see the tree go by, you go, "Oh, look, 100-mile-an-hour tree."
Right? Yeah. I got you.
Right, and that's just relativity.
I got you.
Right, and then you look. Oh, there's a bee. There's a bee flying next to me. Oh my God, I didn't know bees could fly 100 miles an hour.
Dude, the bee's not flying 100 miles an hour. I'm flying 100 miles an hour towards the bee.
Well, the bee's in the car with me.
Oh, okay. So, I didn't know we were in a car, bro.
I'm in a car. I'm driving 100 miles an hour down the freeway. And there's a bee flying in the car with me. He's just chilling, right? That's a 100-mile-an-hour bee right there, right? And it's just relative. It's just relativity. He's going 0 miles an hour relative to me. He's going 100 miles an hour relative to the road, right? And what Einstein is saying is that you can't tell who's actually right.
Yeah. Okay. Fair enough. I thought that quote was in context to not that, or not just that. So okay, fair enough.
Okay. So there's that. I also wanted to show you this. Let me do a screen share real quick, because I think you haven't seen this before. I'm just going to do screen, and I'll just throw that screen up. Share. Boop. Have you seen this before?
Yes.
Okay. So you get the gist of it. The gist being all these little air molecules are bouncing around. And because there is some kind of bias pulling them towards the center, you get a gradient as a result.
Mm-hmm. Yeah.
Okay. Any comment you wanted to make about that?
No. Can you turn it off though? The blue is like crazy on my eyes.
Yeah, I can turn it off.
Sorry. Yeah,
that's fine. If we don't need to cover that, no reason. There was one other example I did want to give you. We've kind of moved on, but one other example that I want to take credit for, because I haven't heard anyone use this yet, for a gas pressure gradient with no container.
Mm-hmm.
Are you ready?
Hit me with it.
Tornadoes.
Gas pressure system with what was okay. Go on.
The center of a tornado is an extremely low pressure.
Mm-hmm.
And there's no container.
Interesting.
Right?
And
you know all too well about tornadoes, right?
Indeed. Let me write that one down as well. That's a good one.
Yeah. And that gives you a whole different field, a whole nother field of things that you can explore and say, hey, how does that work? Hurricanes. And Sean Hawkins is here. How about a wing? An aircraft flying through the air creates a low pressure on the surface. A fan just creates a low pressure on one surface and a high pressure on the other surface. All kinds of stuff. Just the weather in general. Yeah. Just the weather in general is not equalized in pressure. And that's, at least not within the container. And that's where I keep coming back to. And I think we beat this to death at this point. I'm looking at what goes on inside the container.
Mm-hmm.
And you're looking at from outside and seeing the container.
Yeah.
Right.
Yeah, because those are some good examples. But again, my response would be that to even exist to begin with would require the container. So.
Okay. I want to throw another thing at you about that. If you're still hot to talk.
No, go ahead.
Okay. Let me see. I have a slide here. Let me present
okay.
again.
So hold on. I got a question for you from someone in my YouTube chat.
Go.
So it's from James Stackhouse. He says, with the recent Nord Stream pipeline explosion, why doesn't the weight of the water above and gravity keep the gas at the bottom of the Baltic Sea?
Why does it not keep the gas at the bottom of the Baltic Sea?
No, not why doesn't it not? That's not how he said it. Well, I screenshotted it and sent it to you.
Gas that is at the bottom of the Baltic Sea. Is that what he said? That is something that happens. If you take
he said with the recent Nord Stream pipeline explosion, why doesn't the weight of the water above and gravity keep the gas at the bottom of the Baltic Sea?
Why doesn't the gas bubbles up? Why is the gas coming up and not staying down?
Yep.
And that's called buoyancy. Yeah, that's buoyancy. Which means
there you have it, James.
You want to do buoyancy next?
Yeah, might as well.
I wanted to show one more thing. And actually, Flo Rida has a question for you. Let me put it up. By your definition, is a pool a container?
Is a glass beaker a container? If I told you to put something inside of a pool, could you put it inside of it? If I told you to put something inside of a container, could you put something inside of it? Is it a container? Yep.
Okay, so a container doesn't have to be 100% contained to be called a container.
Yeah, no, we covered that already.
Okay, yeah.
I'm with you.
Okay, so a container with a beaker is still a container. Yeah, okay, which kind of blows everything I was about to show, probably. I'll show it anyway, if you don't mind. I'll try to go quick.
Go ahead.
Let's see here. Present my screen. That screen. Go into Inception World. Okay, can you see a PowerPoint?
Yep.
Okay, well, this is what we talked about way back when, the idea of the centrifugal pump, where we have a tube. This is supposed to be a tube. And we suspend it from the center at point C, and then we spin the thing. All right, let's spin it for the crowd. We're going to spin it. Woo! Right? And if we spin it, the centrifugal force will push the air out of the center. You cool with all that?
Yep.
Okay. And so if we do that, we've created a force field through centrifugal force, And we've created high pressure at A, low pressure at C, and high pressure at B. Okay, and then this is where you would presumably say, yeah, but that's in a container. Yeah, it is in a container. And then I was going to suggest, so let's punch a hole and put a tube right in the container there that connects C with D. D is this outside area that's at a very low pressure, like C is at a very low pressure. And then,
just keep going.
As long as the tube is still spinning, will the air at point A escape out to D, or will it not?
Yep. It will escape out to D.
How?
I'll be honest with you. I kind of zoned out. I wasn't listening. I apologize. This presentation just
that's fine. We've been going a little bit too.
No, well, there was some other stuff because we still haven't even talked about the shoebox experiment and why that doesn't necessarily work. Because I feel like you make a big claim about gravity doing something, and in an actual vacuum chamber, it can't be demonstrated. So if you went back to that blue thing you were showing me, if that was in a vacuum chamber, like, would any of those molecules hold to anything? Because it doesn't do that right now. There's no way to demonstrate that now.
Yeah, that's what I'm saying. Let's say we have a centrifugal pump here. We're spinning this, right? Mm-hmm. And we're using that to create a high pressure at points A and B.
Okay.
And a low pressure at point C. And we'll put the whole spinning shebang inside a low pressure chamber. Right? So it's all inside a big chamber. At point D, here is that low pressure inside that chamber.
You're creating another force to prevent, like, to do that, though.
Correct.
Just focus
the air away from C and D towards A and B.
Right.
That's correct. That's exactly what I'm doing. Yes. And would you argue that I cannot do that?
I would argue that that's not what is claimed by the claimed what's happening with the atmosphere.
That's exactly what is being claimed by the atmosphere. Is that a force?
No, because
the force is pulling the air from the low pressure zone to the high pressure zone. That's what I'm doing here, and that's what the gravity is doing in the claim.
Brother, but what you're doing here is you have something in a container and you're spinning it so that it's pressing off the container. So if you use gravity as a container, right, where A is and where B is, instead of a solid line, and you spun that, what would happen?
Well, I don't understand what you're saying. Take out the glass, the tube here, and replace it with gravity?
nothing, because that's what the gravity, right? So
this is what we said earlier. This is how we bumped into the same problem. This is the same problem again, which is I'm talking about the forces between gas molecules. And you can't see the small picture. You're focused on the big picture. There's a container on the screen, and that's all I see.
Hang on one second.
You're seeing it from the container point of view. And no, I cannot make a laboratory experiment to replicate the Earth at small scale. I cannot.
And I think that's extremely important. And representing the larger scale claim, because if it's not happening on the micro, why would it be happening on the macro? If it can't do it, if it can't,
that's one of those logical fallacies to say that if it works when it's big, it must work when it's small. That's not how it works, right? I mean, why would you say that?
All right, hold on one sec. This guy in my chat wants you to put it
back up.
Put the blue graphic back up with the blue dots. 1 second.
Okay.
He's trying to
the blue dots.
Yeah, the thing you were showing me earlier with the blue thing that I didn't like because of the blue color. Okay. I forget what it was called.
Make it smaller or something.
That thing.
Do like that.
Yeah, that's good. All right, so 1 second. So James, in this simulation, they're already assuming that the black stuff is the vacuum of space, bro. Like they already don't care about
right.
that. That's right. Unless you had something else you wanted to add to that. 1 second. It's simulating gravity, bro. Like, you know, their version of it, wrapping it around the sphere and all that. So that's why it's not getting pulled off.
Yep.
Yeah.
Well said. Yeah. Good description.
Yep.
Okay. Let's bring you back to normal. So yeah, recall that. I just like to take us back to the principles that we have agreed to.
Yeah.
If you have a force field that can separate gases by pressure, it can create a pressure gradient. A force field can create a pressure gradient. So that was just stick a pin in that, keep that handy. That's a thing. We agree that that's true. I'll grant you that the convenient way to do so is to use a container.
Okay.
Right? Yeah, we definitely can use a container. You sent me a link. Was I supposed to? Oh, yeah.
I don't think so.
That was that question.
Oh, yeah, that was what
I just noticed it. Sorry.
Okay, so James wanted you to circle back real quick to his Baltic Sea example and say he says, why isn't gravity and the weight of the water keeping the gas down? The buoyancy overcomes gravity in their model, and they don't. It's fine for them.
Buoyancy is a side effect of gravity. The gas is not as dense as the water that surrounds it, and the water is a liquid that is permeable, and it lets the gas, it's movable, so it lets the gas move through it. Yeah. And maybe we should just talk about the buoyancy thing.
Like similarly, James,
we made good progress on the container thing.
Yeah.
You want to go buoyancy for a little while?
Sure.
Okay. I made the claim that buoyancy is the side effect of gravity. How do you feel about that?
I'm sorry, say that again. Oh, the side effect of gravity.
Yeah.
I would say that it's a component of the downward bias. I would further say that a container for it to give form for things to have the ability for their molecular structure to press against another thing is required. Like that, it's a piece of it. I'll grant you that it's a piece of the equation for it.
Okay. Let me screen share some stuff if you don't mind. Let's do that. We'll bring up the density thing. This is from an old video of mine that I still happen to have the slides. Okay, so I go through in this one. We're talking about this topic, right? Gravity and buoyancy. Here's the density tower we love. And then I talk a little bit about what is density, how to define it. Density is mass per unit volume, and we can agree to that, I hope.
Mass per unit volume sounds good to me, brother.
Right, and then I talk about how you would actually measure density.
Wait a minute. Hold on. Can you go back to the density equation real quick? Say, what was it again?
Mass per unit volume. So...
and the P is...
That little rho, it means density. It's a Greek letter that we use for density.
Rho. Okay. So I'm not trying to be a dick, but should gravity be in that equation or no? Because it's a side effect of gravity?
No, density has nothing to do with gravity at all.
I thought you said it was a side effect. Wait, did you?
Buoyancy.
Oh, my bad. I'm sorry. My bad. I'm tripping out. I'm sorry. I thought you said that was for buoyancy. I was like, wait a minute.
We got to start with density to get to buoyancy.
Yeah, you're straight. You're straight. My bad.
I'm just saying, here's a big jug of water. Here's a little jug of water. They have the same density because this one has more mass than that one does, right? They have the same density.
Right.
Okay. And I talk about how do I measure volume, and it's convenient to dunk. If you got a solid object, you can dunk it in some water and measure how much water is displaced to measure the volume there.
Mm-hmm.
Okay. And then how do you measure mass? Well, you just weigh the thing, right? Okay. And then there's a side note about what's the difference between weight and mass. Hopefully we don't need to go there.
Okay.
So let's talk buoyancy.
One sec before we continue. Can we take a comment from the YouTubes?
Comment from the YouTubes.
From Dr. David Banner, and I'm assuming he's a fully licensed and accredited doctor. Says buoyancy is a solid plastic sheet resting on the surface of water, displacing all of its weight over a large enough surface area. Once the plastic sheet is submerged, it sinks from the density.
It sounds like you're describing surface tension, which is not buoyancy. That's my comment to that.
Fair enough.
I mean, we've seen surface tension as well, right? We've all seen that demo. You can float a pin, which is made of steel. Definitely more dense than water. It will float as long as it doesn't break the surface.
So the surface tension of water is strong enough to overcome gravity. See, this is where it gets crazy because all these things are attributed to the strength of gravity, but it's so weak that, you know, all these other things it allows for to overcome it, that it's like it just makes it so hard to accept that that the Earth is a sphere and it's and the strength of the gravity is containing it, because that's part of why we're flat earthers, right? Because all the things that you guys attribute to gravity don't seem to work out in any meaningful way, and it's always like this little tiny baby force that's a side effect of the force overcomes the force that it's a side effect of. I mean, that's crazy, dude.
Well, I don't know. I mean, I do think that's a key part of being a flat earther is to look at the deeper understanding and the deeper learning that comes with studying these things, and to reject it without looking at it, to just say, oh, that's crazy. As opposed to looking at it and saying, oh, wow, that's amazing. Right. Instead of saying, oh, look at that, buoyancy is about to fall out as a result of gravity. But see, you're going to look at this and say, no, don't dig in. Let's just reject it because I don't like that. Right.
Well, it's not that I don't like it. It's that it can't be demonstrated, man, in any way. And then you guys are just like, well, it's too weak and blah, blah, blah. Like it wouldn't, it wouldn't contain. Oh, sorry. Well, go ahead. So
I'm about to demonstrate exactly how it works. And it's really quite easy.
Okay, go ahead.
So I was saying, how do you measure volume, right? You submerge a ball, and then you measure how much water was displaced. Agreed?
Yep.
Okay. And then this diagram, I'm showing that the water level went up when I sunk that ball.
Mm-hmm.
Okay. Now, did that water weigh anything?
Its weight didn't change.
Well, the water that I lifted water up into the air, right? The water was at this level, but now the water's at this level. I raised the water.
Yeah, because you put something that's in its container and it displaced it.
That's correct. Yeah, that's exactly what happened. That water that I raised, I lifted some water. Did that water have weight?
Oh, yeah.
Yeah. So I
misunderstood what you were saying.
I must have lifted a weight somehow by dropping a ball into the water. Dropping the ball into the water has somehow lifted the water. Agreed?
Dude, I'm surprised. Dude, sorry, go ahead. You're good.
Do you agree?
Yeah, I was gonna. Yeah, sure.
I mean, it's
agree.
obvious. It's so obvious, right? That this is a stupid thing to even point out. Really, honestly, right? So let's put it into a different configuration. Let's take the water and put it in a U-shaped tube so we can illustrate this.
All right, one second. Like we got some follow-ups if you don't mind in regards to density. Okay, so yes, keep it right there real quick. So let me scroll up real quick. So net force of the vacuum, one sec. All right. Okay, an object is buoyant only. This is from the doctor again. An object is only buoyant. An object is buoyant only when it can displace enough of its weight over the surface of a medium. Once it is submerged in that medium, it will sink and rise from density. What are your thoughts on that?
That sounds almost right.
What sounds incorrect about it?
And buoyancy is related to the volume of the object, not the surface of the object. If you want this, if you're using the surface, maybe you're thinking of surface tension, which is it's a different phenomenon, works entirely differently.
Yeah, I think, well, his first comment was kind of related to surface tension, I think, but I think the second one isn't. So.
Yeah, so once you're completely submerged, and I'm going to confine the beginnings, at least, of this talk to completely submerged objects. It's easier. And then at the end, if I remember right, at the end, I do a partially submerged object.
All right. A submarine goes down and comes up from changing the overall density of the submarine by adding or removing water from the air, or air from it, or adding water to it. And if it could float on the surface by weight displacement, then buoyant.
Yes, that's dead on. Yeah, that's a submarine.
All right.
Absolutely.
So did he define? Yeah. So So quick question from James, and it may sound like he's being facetious, but this is, because there's two different versions of gravity, right? The bending of, or the result of the bending of space-time and the mass attracting mass. So his question was, which version of gravity is doing this?
James probably missed this part of the conversation. I haven't made any claim whatsoever about what the cause of gravity is. Only that we can observe the effect and measure the effect using good old kitchen scale.
He did probably miss the beginning of it, and you did say that. Totally fair. But can we do a quick sidebar where you give your 2 cents on that, because that's also a thing where we're like, which one are you talking about? So like, could you general relativity figure out buoyancy or no?
Sure, absolutely.
Really?
Yeah, sure. General relativity. I have another video on that, on my feelings about general relativity. General relativity is a minor upgrade to Newtonian gravity. We had Newtonian gravity for like 200 years, and then finally we got a little tweak to it that gives us Einsteinian, general relativity. General relativity is 100% backward compatible with Newton's law of universal gravitation. Every experiment, think about it. Every experiment you ever did in those 200 years between Newton and Einstein all validated Newton. They all agreed this is how it worked. So when Einstein comes along, if he says, no, it doesn't work like that, then all that 200 years of experiments will immediately invalidate Einstein. It would
I think you missed it. I got you, dog. James, the answer to your question would probably be the space-time gravity describes an entirely different aspect of what's going on. When we're talking about buoyancy and all this shit on Earth, we're talking about Newtonian, right?
Well, it doesn't matter. The answer is, it does not matter which equations you use. The Einstein's equations are just more complicated versions of the same equations. They will come out with the same answer. The exact same answer will come out.
So
it'll just take longer.
Okay. So then the same thing you're saying is mass attracting to the center of mass. You're saying that force is also equivalent to the bending of space-time instead of mass attracting mass, right?
I wouldn't say instead of.
Well, how could you not if they're interchangeable? They should be, right?
I would say mass definitely attracts mass. That is not under question. And the way that it does that is through the bending of space-time.
So mass is okay. So well, then that's not. Then fuck. Hold on. This is so confusing.
Not debated. Masses definitely move towards each other under Einstein. Yes.
Well, they only move in one direction though, and that's down.
They move towards each other.
Right. They don't move side to side. Right?
They move towards each other. Whatever.
So
that's it, right? Masses move towards each other under Einstein's equations. Call that what you like.
Let me ask you something. So this is just a total sidebar to what we're talking about, by the way.
We're off on the tangent at this point.
We're super off, but it's interesting because it all goes back to all these different descriptions of gravity we have. So it'll relate in some small way, but it's just okay. Do you just want to get back on the thing then?
If we could get back, because once again, I'm going to stress, it's not what causes gravity that has anything to do with anything. We don't need to talk about that. We don't need to argue about it. We can agree that when you step on your kitchen scale, something causes the spring of your kitchen scale to get squished and the needle goes up. Right? We all agree, no question, that happens. Something pushes down. Right?
Yeah.
Okay. Good enough. That's all we need. Something pushes down. Okay.
Yeah. Sorry about that. He was just asking about that, and that is something that is often talked about in flat Earth. That
it is. And that's a conversation. That's a separate conversation. I really do want to have.
Dude. I hope
detail in the appropriate amount of detail when it's not just Okay. So buoyancy. Back to this thing. I was saying. The rather obvious revelation that when you submerge this object in the water goes up. That water had weight. So somebody has lifted some water. Okay, and let's look at it this way. I'm going to put plungers on my water so the object is not going to sink into the water. It's just going to push down on the plunger with its own weight. The object has some weight. It's going to push on the plunger. Alan, tell me what happens to the water.
The other plunger will go up, right? I mean, you already covered this in the first one. This is just, we can go to the next one.
That is correct. The other plunger will go up, and this water had a weight. And the amount of weight that was lifted is the amount of weight I put on the other side. Right?
Agree. Yeah.
Okay. Welcome to buoyancy. This is what buoyancy is. When you submerge in the water, you lift the water. You must push that water up, and it's pushing back on you.
When you put something in the ocean, dude, see, like you guys think it's displacing around a curve, so
what does that have to do with anything?
Because in your example, again, the water is contained. Like it can't. It's not gonna push against anything or rise or fall if it's not in a container.
Sure, it will. I mean, okay, whatever container it is, a swimming pool, a lake. How big do I have to go before the water is no longer lifted up? In a swimming pool, when you jump into a swimming pool, the water level rise.
It's always going to be in a container.
Yeah. Okay. So we're not arguing about the container. We're talking about buoyancy. Right? Let's just talk buoyancy, and we'll just stick a pin in the whole container thing.
But how could something be buoyant if the medium that it's in isn't contained to be displaced?
Does it need a container to be displaced?
Isn't the whole thing of your argument that the weight of the thing is displacing the water and it's making it go up though?
I'll say it again. If you dunk a ball into a beaker, the water goes up.
Right.
If you
Because
dunk the ball into a swimming pool, does the water go up?
if you dunk the water onto a puddle you pour on the table,
Well, it would have to be a puddle deep enough to submerge the ball, right?
and
Has to be
would that
deep enough to
would
submerge.
that deepness have walls like a container? Like dude, see,
Sure.
like I swear to God, I'm not. I
Put
swear to
some
God, I'm not
container.
trying to. I swear, I'm not trying to like do that to you, man. Because
I
I
understand.
hate when they do
Container
that.
is a
But
thing.
it's
The
so
container is
hard
really going to
to.
be a mental block. So just put it
It's
in a
so
container.
hard.
That's fine. Put it in a swimming pool.
Put the container in a container, bro. Like, come on, dog.
No.
You're killing me, bro. You're killing me.
Do the whole thing in a swimming pool. Right? You agreed a swimming pool was a container. We're doing it and we're not talking about something that does not have a container. We're talking about a swimming pool. We're doing buoyancy in a swimming pool. Okay. Is that cool?
I don't understand. Yeah, but I don't understand how you think a swimming pool is not a container. Is that what you're saying?
No.
That eliminates the container factor?
No, that's the container you're asking for. You kept saying, "Where's the container? Where's the container?"
No, I know where the container is at in your
example. No, I don't believe there's no container.
Well, no, you believe the container is like the water wraps around the sphere containing itself. That's what I meant by that. It's like in your slide, like what I'm saying is
But that's not the topic right now, and we know that it's a stumbling block for you. So I think we should just not talk about that.
Okay. Let's move on.
Are you trying to suggest that the buoyancy I'm about to describe here, the buoyancy I am describing, won't work without a container?
Correct.
That's what you're trying to say. Okay, that's not what the math shows, but that's kind of advanced math. So
hold on a sec. You guys are real big on that's not what the math shows. But what is what does demonstration show? What does reality show? What's within our physical ability to demonstrate and test with ourselves?
You want me to scale it down. As soon as you ask me to scale the problem down to something smaller than a planet, I'm going to need a container in order to scale it down. And then you're going to say, see, you got a container.
Well, no, I'm just happy that you said that, man, because a lot of that's fine. I'll accept that answer. Totally fine.
Okay, cool. We were just talking about buoyancy, right? What is buoyancy and how is buoyancy a side effect of gravity is the topic. What I'm showing with this slide is that the ball pushes down on the water and it necessarily is displacing its volume of water from whatever the water wants to go down. The ball is preventing the water from going down through its own weight, right?
Yeah.
And the water is pushing up on the ball. The water is trying to get under the ball. The water wants to go down. So that means it's trying to get under the ball and push back up with its own weight.
Mm-hmm.
At this point, the ball's not moving, right? Once the ball is settled, the forces are equal.
Agree.
Okay, so the force acting down is the weight of this ball. And the force acting up, therefore, must be equal to the weight of the ball.
Agree.
Okay, so where did that force come from? It came from lifting the water on the other side. So this is not analogous to a full planet. This is not a planet we're talking about here. This is just buoyancy in the laboratory.
Right.
Okay, so that's a little different from this where we submerged the ball and the ball's sitting on the bottom. But that this water that we lifted still wants to get underneath that ball. And it's going to try to get underneath the ball with a force equal to its own weight.
I'm sorry, say that last part again.
The amount of force that this water is pushing down with is its weight.
Yes.
And it's trying to get under the ball. But in order to get under the ball, it would have to lift the ball.
I don't know that it's trying to get under the ball, brother. Like it just got raised up a little bit. I don't know that it's also trying to come
Well,
back down
if
under
the
the ball
ball,
and lift it up and shit
if the
because
ball
it can't
wasn't
do that,
there, the
right?
water would go back down.
Right. So it's not. So it
I'm
can't
not
try to go back down
describing,
until.
I'm giving it like human motivation or
Well,
something. No, that's not what I
well,
mean.
no. It's not what I mean either. Before it can even try to begin to go down, the thing would first have to be removed. So it's not trying to do anything. It's found its resting place,
Well,
or whatever.
it is stabilized, but in this stable condition, there's an amount of force pushing up on the ball exactly equal to the weight of the displaced water that we see from this diagram. We see that when the ball pushes the water up, the water pushes back with an equal and opposite force. That's, just Newton's third or whatever, right?
Right.
And that's still happening here. The ball, when
Okay.
you dropped it in, the ball pushed the water up. It lifted it with a force, and it's holding it up there.
There's not a force holding anything up there, though. The thing you put in there is
Yeah,
holding it
there
up
is.
there.
Yes.
No, the
and
thing you put in the water is holding it up.
You can't lift something without force.
Yeah, the force is the displacement that's being pressed against the container when you add another object into the container to take up space.
The force of upness does not come from the container. The container cannot push up. The container only pushes in.
It's a component to it. Let's see. It doesn't. Yeah, but the water wouldn't be able to rise if it wasn't in a container to have walls to climb, right? So
correct, but the up force needed to climb that container came from the ball pushing the water out of the way.
Oh, I see what you're saying. Okay. Yeah. Sure, man. Let's move on.
Okay. That is it now. If we just calculate how much water was displaced, that's the volume of the object.
Sorry, say that again. I was reading comments. Say that again. Sorry.
Yeah. The amount of water that is displaced.
Oh, yeah.
Is the volume of the object.
Correct.
The weight of the water that was displaced is gravity times the density of the water times the volume that was displaced.
So
that is weight. Weight is mass times gravity, right?
Mm-hmm.
Whatever gravity is. Well, I'm not saying what it is, just it's a constant.
Yeah, no, I'm with you.
Okay. So if you submerge something in water, that submerged thing will weigh less than it does in the air. By how much? By the volume of the object times the density of water times gravity. That's how much less the object weighs when underwater.
Yeah.
And why is that? It's because the water has weight. The buoyancy force is the weight of the water, which was caused by gravity. Without gravity, you'd have no weight for that water and no counterweight pushing that ball back up. And then in this next slide,
well, like
go ahead.
what you're, yeah, I mean, this is what you guys, yeah, I agree.
This is what you guys say, but
I mean, this is what
about that is at all like, no, that can't.
No. You're just kind of like reteaching the, like I know this, like I don't. What was the point of this presentation?
What is the point of this presentation? The point of this presentation is that buoyancy is not a mystical force that fights against gravity. Buoyancy is the side effect of gravity. Buoyancy was caused by the fact that water has weight, which Water has weight because of gravity. That is the amount of buoyancy. The amount of buoyancy is the weight of the water that you lifted.
Right.
So if you are less dense, now I'm going to show one that's less dense, the ping pong ball floating on the top there. If you're less dense, then the water's weight would be more than your weight for the same volume. And so in this tug of war, right, if we go back to the tug of war thing, the water would weigh more now than the ball does. And so it wouldn't push as much. It would just push a little, right?
Mm-hmm.
Not enough for the ball to go all the way under. And then on this slide, I do a calculation. I show how we would leverage that, like in a physics class, how we would leverage that to answer a physics question, answer an engineering question. How do I make a boat that will float?
Hey, speaking of floating boats, how did they make floating boats before they had the G part of the buoyancy equation?
Mostly by trial and error, I'd say.
They just wung it.
Yeah, I would guess. I don't know if you go back way back. Archimedes' principle is very, very old, though.
What's that?
The Archimedes' principle.
Shout out to your boy Archimedes.
Yo, Archimedes! Archimedes' principle is the one that says the amount of water you displace is your own volume, and the weight of that water is the buoyancy. It's just basically Archimedes' principle. I'm misquoting it here. Maybe somebody can give me.
Yeah, gotcha.
It was,
okay, yeah. So trial and error.
He got in a bathtub. Like you fill the bathtub right to the top. He gets in the bathtub. He sees that the bathtub overflows now, and he immediately puts it together and says that the amount of water that's overflowed is exactly my volume. And then he says, okay, if I'm floating in the bathtub, right, I'm floating, then this bathtub together with me weighs the exact same amount it did before I got in.
Yeah, no, I got you. Archimedes. Okay. We're good. I just hadn't heard of that. Lots of principles, to learn.
It was a really, really long time ago that was discovered. So, boat people, presumably boat engineers and designers knew about that, I guess. I don't know if they ever calculated it. I think they learned to craft, right?
Yeah. So, I was thinking, because it's like, if you were going to build a boat, because, you're building like a warship or something to explore and whatnot, and then like, oh, you accidentally didn't build it right to, because you're overweight or something. Like, it just seems like they would have had to have come up with a better way than trial and error. To consistently build boats and stuff. And
yeah, I think that early stuff was all handed down by craftsmen, year after year, generation after generation, and just iterated on.
Sure.
And sometimes people had a great idea for a boat that totally didn't work well, So, okay, long story short here, all of this comes down to, for me, the U-shaped tube is it. And what it shows us is that the reason there's a force pushing up on this ball is because that water has a weight. The amount of that weight is the buoyant force. And you can put it in all the equations, and that's going to work. And if you browse my gravity section, or my Science for Skeptics section, I think this is from my Science for Skeptics series, I suggest some experiments that you can do to show that that's the case, right? That buoyancy is not canceling out. That's another one that's rather interesting, actually. Buoyancy does not cancel weight.
Oh, really?
Right. Like if you take a cup.
I've never heard anyone say that.
Oh, okay. You never heard anyone say buoyancy cancels weight?
No, okay. I've just heard that buoyancy makes things float, not that it cancels the weight of the thing. I've never heard that.
Okay, cool. So yeah, meaning you do understand then that the buoyant force has to come from somewhere. Something else is pushing down by the same amount that gets pushed up. And
Yeah.
that thing that's pushing down is the weight of that medium. So if you want to put helium, right, you want to put helium now in air. Why does it float? It floats because the air is being pulled down harder than the helium is being pulled down. The helium is also being pulled down, just not as hard as the air is.
See what? And it's not being pulled down as hard because it's well, you said it's not fighting. Well, you said it's not fighting buoyancy, but I guess it kind of would be then, right? If it's pulling down on helium, but the density is overcoming it, they're in a bit of a tussle, yeah.
Yeah, sort of. Yeah. When we write the equation out, we'll put the buoyant force as a negative, and the weight force as a positive, and add those two together. So you could call them, fighting, sort of. I suppose. But
who do you think would win in a fight, density or buoyancy, dude, or whatever we're talking about, or gravity? I can't even remember. Gravity or density, dude? Who do you got money on, dude? Gravity.
Gravity always wins on the big scales, right? On
Allegedly.
the small scales, nuclear force wins. But
nuclear. I thought
scales, it's all about gravity.
Yeah. What's the what'd you say? The nuclear force?
Yeah, the strong nuclear force.
Oh yeah, dude, I haven't got the strong force yet. I'm still on that weak force. What's up with that strong shit?
Yeah, strong is even stronger than the weak.
Yeah.
Yeah.
What's the nuclear force? I haven't heard of that.
Oh yeah, I've
heard of strong force, but I haven't looked into. I've never really heard anyone mention it, so I haven't really looked into it. Can you touch on that real quick?
Well, it's just the electromagnetic force, the electrostatic force keeps the electrons stuck to the atoms, right? Stuck to the protons, stuck to, orbiting or whatever you want to call it.
Yeah.
And then you say, well, how come why are the protons sticking to each other? They shouldn't be doing that. And then there's why are the quarks sticking to each other?
Let me ask you something real quick. Are quarks real? Have you guys seen those, or is this a math concept? Because I haven't touched too much of that's from quantum mechanics, right? Quarks and bosons or something like that.
They're subatomic particles. Yeah, I mean.
Yeah. So you guys seen those, or what's up?
I mean, what you see, you can't see a quark.
Shit, dog.
You can't see a quark, right? You can't hold it in your hands and say, "Oh, look, a quark." No, there's a quark.
Right. So what? But what are we talking here?
That's not how you science stuff. You don't science stuff by saying I can see it or not, right?
Yeah, fair enough.
I can't see it, therefore it doesn't exist.
Yeah. So the big force or strong force you're saying is electromagnetism?
No. The gravity is the weakest force, but because it has infinite range on large scales, it wins. And then on smaller scales, it's all about the electrostatic force. That's what all chemistry is from, the electrostatic.
Yeah, the right. So have you heard that? I'm sure you've probably seen it from some flat Earth videos or something. That clip of Professor Walter Lewin from MIT talking about I forget what it was, but how everything on Earth is dictated by electromagnetism and all that, and then only when you go to the quote unquote large scale is when gravity overpowers that.
Yeah. I'm just ripping off Walter Lewin here, totally.
Yeah, he seemed like a cool guy.
Yeah, I liked him a lot. There was a scandal, though, unfortunately.
Oh yeah, I heard about that, dude. What are your thoughts? Is it guilty, not guilty?
I don't know.
What did he even do? What was the accusation?
It's tragic that there was a scandal with such a well-known person, a well-liked communicator. I don't know, and it's not up to me to know that.
Oh yeah, I don't even really know what it was. I just recently heard that there was a scandal. Haven't looked into it. I just heard him through because
it tainted all of those awesome lectures that we love.
Yeah, it's a real shame when that happens, man. I forget what it was recently. I found out something about someone I watched, and I was like, oh, well, that's a shame. You know, can't really continue watching them. So, yeah,
So,
sucks.
what do you want to talk about? Anything you want to talk about before we?
Yeah, I got a couple comments from the doctor in the chat, and but they're
Okay.
related to gravity. If you want to touch on that real
What does
quick,
Dr. Banner want to talk about?
Dr. Banner
make
would like
him angry.
to.
Don't
Yeah,
make him
dude.
angry.
Is
Yeah,
that who the Hulk is?
Yeah.
I knew that it was a reference to something. I couldn't remember which doctor. I know there's like Doctor Strange and Dr. Banner and Dr. Bruce, and well, Batman's a doctor, right?
I don't think so.
Oh,
I don't think Batman ever got his doctorate degree. Okay,
unlucky.
so you linked me something here.
Yes, let me scroll up here. He had a couple. So okay, so back to density real quick. He had a question about density or comment on density, and then gravity as well. So we'll start with the density. 1 pound, a 1 pound cube of gold and a 1 pound cube of iron weigh the same and displace the same amount of water. Yet the gold sinks in mercury and the iron floats.
No, that's not correct. They
Well,
don't displace the same amount. No, they have different densities.
Now, when you say displace the same amount, if you back to the
1 pound of gold and 1 pound of what was the other material?
Iron. 1 pound of gold and 1 pound of iron displace the same amount of mercury. And
they displace the same amount of mercury.
Yeah, my bad. I thought he said water. Display the same amount of mercury, and they both weigh 1 pound, but the gold sinks and the iron floats.
Okay.
So let me see if he has any follow up to that.
The density was in that equation. You saw that. Right. Just punch it in. just punch it into the equation, and you'll see what happens. You'll see that iron definitely floats in mercury because it's less dense. Because mercury has weight, and so does iron, and no one would argue that they don't. So whoever has the more weight per unit volume will sink in the other. But it comes down to the weight per unit volume.
Cool. Yeah, I'm not sure where he was going with that, but he did ask it, so I figured I'd read it. And then he had one more. It was about 1 second.
Yeah, they wouldn't displace the same amount as Sean is saying. No, they wouldn't, because the iron wouldn't be fully displaced.
Or like you mean fully submerged?
The gold would be the gold would be fully submerged. So not all of its weight is being canceled, right?
Sure, I see what you're saying.
The amount displaced would be its volume, but
it doesn't cancel weight.
The amount displaced of the iron is the amount that it
pushes into the water. No, I got you. It makes sense. I'm with you. All right. So he said, says two masses with the same charge will never attract to one another. They will be repelled. They will instead be forever repelled from each other. Gravity is disproved with physics. And then more on that, he says, only masses with opposite charges will attract. That's how
electrostatic force works. And we can see that the gravity force works differently. And as I stated many times, we don't have to get into what causes the gravity force, but we really can't argue that it's there. There's something creating a force. When you step on the scale, the spring compresses. Would anyone argue? So does it take force to compress a spring, or does it not take force to compress a spring?
Yeah, no, I don't think that's in dispute.
So there's a force.
So okay, so his follow-up study.
Say right here now, anyone tells you there's no force, the spring compressed. That person sounds like an idiot to me.
I thought we were talking about planets attracting and stuff.
Things. Okay. Can they attract? I don't know where. I don't know. I didn't say where the force came from. Right.
So anyway,
it definitely exists.
Let me continue on with what he followed up with. Okay. Gravity doesn't exist at all, or doesn't exist for all masses with the same charge. 1 second. All of the masses are in fact repelled from each other. It's a bad day for the globe team when the size of the masses makes no difference, and then they're the same mass, and then that means that they're the same charge and they will repel each other forever.
Okay. Again, if you need to get into the mathematics of it,
well, I think you're saying that
forces work the way where like charges repel, and gravity forces, if that's what you think that it is, like if you're going to take the mainstream, what gravity is, like charges attract, and that's how those forces work. And simply saying that because electrostatic force works this way, gravity must also work that same way. That's just a logical fallacy. That's just like, why, right? Why does one force have to act the same way as the other force?
Well, I think what he was getting at was that it would repel and it would override the gravity. But I guess your contention would be that it
doesn't repel.
It's stronger.
We measured it many times as an attraction. Right? Orbits don't happen because planets repel each other. Right? I'm just talking the mainstream.
Well, if they're
arguing about what causes gravity, but
no, I know. Well, I thought this was like an afterthought to the stream or whatever. So
afterthought. That's cool.
Yeah. So
it's just
we'll come back. We'll come back and do a gravity thing because I want to touch on general relativity, black holes, and all that again. And let's see. So yeah, we'll come back to that, David.
What else did you have? And anybody in my group want to jump in something? We can see.
Yeah, I think that's about it for now. I'm glad that we were able to get together for the vacuum situation, because going back and forth over days with emails was, I mean, dude, like I like you, but it was getting super tedious. I was like, can we just talk? I'm glad you asked.
Yeah, it was kind of going nowhere. But yeah, I'm really pleased. Let me wrap it up. I think we came to a place where we basically agreed that the globe model does not need a container.
You know how I say that it's consistent with the lore or whatever. Yeah. So I would say that it's consistent with your guys' lore, and that arguing over it is kind of fallacious. Unless we can prove something more than what we can, because we can't, go to the quote unquote edge or go up high enough to test if there's a firmament and all that. But it seems rather implied from our position. But yeah, I agree that what you presented is more consistent with what you're with the lore than I originally thought.
Okay. And then and we didn't really get to talk about your box thing. The like, why doesn't the air stay down in a small box if it stays down on a giant planet?
Well, you don't even have to really address it, because your point that it was what was it? Like, you guys don't even think that it would happen on the small scale, so it's not an issue for you guys.
I would actually say no, it does happen on the small scale. It just happens to a small amount on the small scale.
Measurable or no? Or hypothetical?
Absolutely measurable. I mean, every cell phone, I don't know, like lots of cell phones have pressure transducers. You can just ask what is the barometric pressure?
Mm-hmm. No, I thought we were talking about that.
Get a different pressure from that much.
I'm sorry. I thought we were talking about the.
But no, that is
right. But
where we differ is that you guys talk about, we put it in a vacuum and we let it out and all the air escapes, and I'm gonna say, no, the air gets into a gradient.
Right, and then our contention is that the gradient prerequisite would be the container. So, in your example, you would be overlooking the fact that you're already in a container.
Right, but then where we came together
from our perspective, yeah, right.
On a sphere, you actually don't need the container because it goes all the way around. The gradient layers are concentric spheres.
Yeah,
they don't need to be contained on the sides.
Yeah. All right. Well, can we do a quick Cavendish before we wrap up?
Yeah, sure. There's people shouting about Cavendish in this thing.
Oh no shit! On your side too.
Yeah. Although Jez says is the best. He says Cavendish is dead. He doesn't move.
Dude, Jezza, dude, what up, man? And yeah, so dude was saying that the if you did the Cavendish experiment with 2 stone balls instead of lead balls, that it wouldn't work. If density is what makes
Who
sense.
said that?
David Banner.
Awesome, David. Why don't you build it? Show us that.
I
can show you videos of I can show you videos of lead attracting lead. Lots of people do that one. I can show you bowling balls attracting lead. I can show you Coca-Cola attracting lead. I can show you sand attracting water. Those are the ones that I have, like that I have definitely seen and used.
Sand attracting water. Do you have a link to that? Water. Do you have a link to that one? I'm interested in that.
Well, that's somewhere in my gravity series. Let me see if I actually have like that clip sitting here. It's one of the older ones, so it would have been on an older computer. No, I would have to get you the from my YouTube.
Yeah, send me that one sometime because we're used to a bunch of stuff that we highly disagree with. I don't think anyone's seen the sand and water one. That sounds really interesting.
Yeah, that was actually a really good one too. He also showed electrostatic force in that one because a lot of people say, "Oh, what if it's electrical?" Right?
Well, some of the other points of contention were like, the temperature of like the environment that it's in, the temperature, because contraction and expansion and all that sort of thing. Like there's tension in the wire, tension in the frame. All sorts of different aspects that could produce that or whatever. So
yeah, absolutely. And lots of people saying things like temperature, electrostatics, different materials, blah 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 blah. Ultimately, I'm going to say it doesn't matter. First of all, the material thing is kind of silly because whatever materials you put in there, it works. So materials attract materials, right? And the electrostatic thing is super silly because if they're attracted from electrostatics, then that's gravity. Fine.
I would say that materials appear to attract materials only when they're hanging from a tension bar and all that. Like my bottle of water isn't attracting the tissue box next to it,
Not to an amount you can measure.
Not to any existable amount that means anything or that could be represented in reality. Like you can claim
those aren't cartoon words, right?
Measure
the amount predicted. You could say, what does mainstream science say?
You could mathematically work out what it should be, but you don't know that it's actually doing that, bro.
No, I don't, because the amount predicted is so small that I could not possibly measure that. So this is your logical fallacy again, right? My inability to prove that it's there is not proof that it is not there.
But you claiming that it's there, like if you were to get back into the logical fallacy, which, I'm sure you don't really want to do, but the burden of proof would be on your positive claim, yeah?
And I have the Cavendish experiment for that. Done. Right? Now it's on you to say that is incorrect for some reason, not it could be maybe incorrect for reasons that I have yet to explain.
No, because
right. You have to say specifically, it is wrong in this way. I have shown that it is wrong in this way. You can't just say it could be maybe wrong because of reasons.
No. Okay. So in your mass attracting mass experiment, right? Because we talked about this one time and I said, is there any way you could bend light, based on the mass of something, right? And you said, unfortunately, that would only be possible with celestial objects, right? If you remember that.
You can do it with celestial objects.
So And then I think the Arthur Eddington eclipse stuff was one of the biggest proofs of general relativity, right? Because that's what he essentially proved,
Yeah,
or
probably the
allegedly.
earliest one. Yeah.
So have you heard that a lot of his data was omitted and stuff, and they kind of cooked the books on it? I haven't looked into it yet myself, but I'm about to dive into it. I mean,
dive into it. Let me know if you can find anything like serious on that, and let me remind you, please look at both sides.
yeah, no, that's why when I find it, I'll send it to you, and we can talk about it. Because yeah, that's the stuff I'm interested in talking about. Because yeah, like I said, I've been reading papers and stuff, and then asking you like how it compares and contrasts with the official narrative and stuff.
Right. These days, it's much easier to do. We have better technology. We can measure the gravitational redshift right here on Earth, just caused by the Earth's gravity.
Well,
that's been done.
The redshift of what now?
The gravitational redshift, as in gravity is pulling on the light. We can measure that right here on Earth now.
Interesting. Yeah, because I was looking recently into if you could measure the redshift of the sun or something, and they were saying you can, but it's like 10 to the negative or 10 to the negative 17 of like whatever they have measured. So it's like super small, insignificant. You would think it would be bigger because the sun's closer or whatever. And I think the same was for the moon. I didn't even look at the moon yet. So did you know if it's possible to redshift the moon or anything like that?
Does the moon move towards us and away from us at any kind of speed that it would shift? Does it just kind of go around? Stay at approximately
so you're saying if you had like a station set up that you couldn't observe the moon like moving around? Well, I guess no, because we're rotating too, huh?
I'm not sure exactly what you're asking for. If you want gravitational,
you can't come up with.
I'm sure you could measure that. It's a lot smaller than here on the Earth, but you could probably set up the same equipment that they did here to do it.
Yeah. So yeah, well, I'll get back to you on that because like I said, I haven't fully looked into all that stuff. This is just some stuff I was coming out just recently, started looking into. So all right, cool, man. So
well, on the Cavendish, I wanted to leave you with one thing, and that is I do have a video on my channel about the Cavendish experiment, and the highlight is if you think it could be any of these reasons that it's temperature, electrostatic, whatever, blah blah blah, then wouldn't that mean you'd get different results every time? When different people do the experiment and different people use different materials and they're different sizes, different places, they would, if it was error, you would not get the same result.
So are you making the firm claim that they all get the same result?
I would put it to you. Go show me the variation. Oh man, I don't have it. I thought I had it. Yeah, I don't have it. You'd have to watch my video to see it because it was on my old computer. But yeah, I would put to you what you should do. Go find the variation. How much variation is there? Because they don't all get the exact same number, do they? They get different numbers. How different are they?
Bro, but when you're talking about something that's that small, because isn't it like, how small is the number? Isn't it like 10 to the 18 or something like that? 10 to the 9? It's super small, right?
It's dinky. Yeah.
Yeah. So like when you're talking about something that small, any variance really is huge, right?
No.
Why's that? How do you figure?
Because we would do variance in terms of percentage, right? You would say, does this vary by 1%? Does this vary by 2%? Does this vary by 100%?
Do you happen to know the percent variance?
I don't know. I don't know.
Yeah, we should look it up because
in my video, I have a graph of it.
Yeah. But you've looked into it though. Like you've seen the difference, right?
There were some flat earthers who were making the claim that the value is just all over the place, and there's a certain legitimacy to the claim, in that the accepted value is outside the range of some of the modern experiments. Some of the modern experiments don't give the same value that we consider to be the correct value. And then you say, that's broken, right? That's science is broken.
What do you chalk it up to, the invariance? Just user error?
The experimenters have grossly understated the error in their experiment is the most likely explanation. Right? It's like when you say it's definitely in this zone because I was super careful. Go like that. Right?
Yeah.
The rest of us out here in the real world go, yeah, right, dude. Right. You were super careful. I really believe you. Why don't you just like, and then we're good.
Sure.
Yeah. And that's the thing, because when you see the chart and you're like, oh, look, these numbers are all over the place. It's because you're zoomed way in on this tiny little number. Zoom back out, because keep in mind, your contention is that the correct number is 0, right? That there is no force of attraction. Not that they're measuring the force and the force is wrong, but you're saying the correct force. If they did this correctly, it would be 0.
Yeah, I don't think that mass attracts mass in the way you guys describe it now.
Right. So thousands of times this experiment has been done. They never get 0. They always get, there's some wiggling, but it's all in a tiny little range, not 0.
Yeah, I guess the common rebuttal to that is that, or that I've heard rather, is that everything intrinsically has the capacity to have a static electric charge, and because you can't isolate that, blah, blah, blah. What are your thoughts on that?
Static electric charge is always the exact same amount, is what you're suggesting. The amount of charge is the amount that cannot be eliminated.
Yeah, I guess it would have to be, huh, if that was the claim.
And then,
touche, let me write that down.
Let me circle it right back for you.
It's a good point.
That's the case, that there's this certain amount of static electric charge that you can never get rid of, that is always there. That's gravity. All objects are attracted by this static electric force that's always there, that you can never get rid of. You keep measuring it over and over again. So now you just proved that all masses attract.
Mm-hmm. Yeah, it's fair
right point. Back to it. So it's not an argument. It's just a red herring. That's one of those things that I like to call a red herring, because it's an excuse to try not to acknowledge what you see with your own eyes, which is that the masses are attracted. And you say, oh, they're attracted by electrostatic. Shrug. Okay. If that makes you happy. Okay. They were still attracted.
No, that's a good point.
Right?
It's a good point.
And then if you were really serious about it, then we could just, if you really believed that, we would reverse the polarity on the charges and so forth and show that that's not it. Super easy.
Oh, dude, that's really good, actually. 1 second. Write it down. Could change the charge. They would repel, right? Change the charge, and then they would repel at the same amount.
Oh yeah, I mean, just put 110 volts on the whole system, and then it'll repel, right?
Mm-hmm. Yeah.
And put negative 110 volts, it'll repel. Short the system, ground it to each other, and they'll stop repelling, right?
Yeah, no, totally.
Put a Faraday cage between them, and they won't repel anymore. And that's actually a demo in that video. I'll try and send you a link to it later. Is electrostatic gravity now? Some people have said so. Some people have made that claim. I believe I've seen Bob Nodell make that claim. I think it's pretty trivial to show that that's not the case, but it's irrelevant to our conversations for tonight.
Yeah. Well, if you if you want to go on a little longer, I'm interested in hearing why your arguments against it.
Okay, well,
real quick. Like it doesn't have to be like a full blown discussion or anything. I'm just interested in what your perspective is on it, because we had or not we, I'm not part of it, but Jaren and Whitsid and Dearth and stuff had somebody on recently, a professor. Or did you see that?
No, but it's those guys, so
Oh, I mean, it was pretty cool though. They had a guy on that was he was saying that he disagreed with the static electric stuff, but he really didn't give much of any good explanation as to why. He just was circularly going over it. So what are your thoughts on why it's not viable?
Okay, if it were a static electric charge, then differently charged objects would have different weight. And we're done.
Differently charged, dude. Phenomenal.
That's it, right? Rub a balloon on your head.
No, totally.
A static charge. Does the balloon weigh different now? And we're done. It's like there's really no reason to entertain these crazy ideas if you're not going to just put it to the most obvious boneheaded test, right? Do a test.
Well, hold on a second.
Right? I mean, how hard was that?
When you say rub your hair on a balloon, and then what? The balloon just weighs more? Like then if you put it on a scale?
Does it either weigh more or less? When okay, don't rub a balloon on the, just blow up a balloon, put it on the scale, weigh it. Now rub it on your head.
Right.
Weigh it again. Does it weigh different?
I don't know, will it?
Well, if it's electrostatic force.
Oh, then it would, yeah.
It must, because you have added 10,000 volts to this balloon, right? There's a huge amount of electric force that you've added to the balloon.
You know what though? They've shown demonstrations where they add charges to stuff and they make it like levitate or
Well, sure. If you put it in an electric field, if you deliberately build an electric field and then you
have you heard of a Van de Graaff generator? I don't think that's that an electric field?
Yes, it's a static electric generator. A Van de Graaff. Yeah, grab yourself a Van de Graaff.
Yeah, so you can manipulate and overcome gravity with that.
Put your hand on the Van de Graaff and watch your weight just melt away because.
So, but have you seen where you can make stuff like levitate when you change its charge and all that? So I think that is a component of it then, right? Doesn't that prove that?
Electrostatic force can create levitation. Yeah.
You can make something levitate with sound, actually. Have you ever seen that?
You're saying sound that's what weight is, right? You've got to take all my weight out by adding whatever charge. You're saying whatever charge is on me is the charge that's doing it, right?
Mm-hmm.
So how much charge is on me? Mm-hmm. Guess what? 0, right? It's 0. So let's put a volt on me. Okay, I got 1 volt on me, and I weigh 150 pounds, right? I got 155 pounds from 1 volt. I'm going to attach myself to a Van de Graaff and crank it up to 30,000 volts. Shouldn't I weigh 30,000 times as much now?
You know what? Excellent question, dog. And I will be asking that to the people that have a Van de Graaff generator in the FE community. So.
Because maybe I'm going to weigh a tiny different amount, but if you're expecting that voltage to be the entire force, we need a lot of it. And it's just not there. And if it was, then, just take one thing positive, another thing negative. Do they both fall?
Mm-hmm.
Right? When you take a piece of silk and a glass rod and you just rub the silk on the glass rod, one of them becomes positive, one becomes negative.
No, I'm with you.
They both still have weight. Mm-hmm. So you've actually reversed the charge on one of them, right? But you didn't take away its weight. So
yeah, well, I mean, we'll have to get into how much charge is required and all that, but
anyone would even listen to that, right? Why aren't we just done talking about it as soon as somebody says, rub a balloon on your head, it still falls to the ground?
Well, if you rub a balloon on your head and stick it to a wall, that little force overcomes gravity.
Uh-huh.
And you're saying that same gravity force, is a barrier to the Earth against a low pressure system. Like that's where there's a huge point of contention, because it's you're back
to that, right?
No, I know, but because it's all connected, right? Like it just makes, I don't know. It's just, it just doesn't really make sense if it's not. And then
Rach maybe has some insight into how this is supposed to work or something. I don't know. So the claim is that negative isn't negative. Everything is positive, and there's no such thing as negative, or something like that. I don't know. It's really silly, whatever it is, because I
know what he's talking about. It's not that. It's
okay.
It's not quite that. It's close, but it's not quite that. I don't know what it is off the top of my head to repeat it accurately, but yeah, it's close.
Ground everything to try to keep it electrically neutral.
Yeah,
with the ground.
I'm with you,
but we're still stuck to the ground. So
totally with you.
I'm gonna say no.
Fair enough, dude.
And it doesn't mean that there's no such thing as electrostatic charge. There's absolutely electrostatic charge. A balloon sticks to the wall. We know that.
Right. It just seems like you guys attribute a lot of strength to the force, and it seems to be overcome by literally like anything. Literally anything.
That's a key point. It's a key point, Alan, and I'm going to say the same thing I think I said before, which is we don't treat forces as just mystical, magical things that just do whatever we feel like they should do. We study what actually is observed in the real world. We write that down. And then we say, if that what we just saw, if that's true, what would this do? What would that do? If this that we just saw, if that law is still true, how do boats work if that law is true? Oh, look at this. This is how boats work. Hey, that is how boats work. Cool. What about balloons? Would balloons work if that law was true? Oh, look, it works. And only when that keeps working do we accept it. As soon as we say, you know what, that law, it doesn't match our observations. The moment that happens, we say, okay, there's a limit to the law. You can't apply the law in that area. It's not working there. We'll have to do some research. Right? I mean, gravity's not new. So,
dude, we'll have to do some research. Yeah. Dude.
That's where, as soon as the law, when you've got a law that you've written based on observations, Newton's gravity is based on observations.
So Newton's gravity based on observations, when you guys observed, not you guys, you didn't do it, but I really hate when people are like we and us and we know like as if they were involved in it, like they got firsthand knowledge of the shit. So I hate talking like that. So anyway, that's why you're fine. But anyway, so when Newton's you guys established and written down the laws of gravitational forces from Newton and stuff, right? But then it was observed that certain galaxies rotate too fast, and then. So did anyone go back and do research on the fundamentals of the theory, or did they just invent a variable to account for the faster spin?
It's a good question. The first thing that happened was the scientific community said, no, you messed it up. Go look again. And everyone just kind of was like, that's weird. You messed it up. And then people looked again. And then when they found it again, they're like, okay, maybe there's something to this. And then a million different theories were put forth.
And now, Would it be fair to say that the theory selected to explain it, like, just so happens to be like carefully tailored to GR?
No, that's not fair. The way it has happened, like you're talking about, like dark matter, right?
Mm-hmm. Yeah.
So the original astronomers who discovered it, Vera Rubin and Fritz Zwicky, I would call out.
Shout out to Fritz.
Fritz and Vera. don't diss Vera. She was huge. They discovered it in two different ways, and so when you have confirmation of it from two different measurements, it looks pretty serious, right? Mm-hmm. And so that has created a flurry of scientific interest, and you're kind of characterizing it as if it's already been boiled down to one thing. We don't know what it is. We still don't know what it is.
Does a variable exist to account for it or not, even though you don't know what it is?
No. There's no single accepted solution for it. It is still unknown. It is active research. Some people believe, or I'd say some people suspect is a better word. Some people suspect that Newton's equations, or really Einstein's equations, are and need a tweak, that they're not correct, that there's something in there that we've missed. Some people,
dude, I know a guy that's got something to say about general relativity, and it's math.
That's called MOND usually, which is modified Newtonian dynamics. They still call it Newtonian dynamics, but they would be talking about GR. So some people are looking at modifying the equations that we use for gravity to see if we can come up with a better model of gravity that accounts for those things. Other people were looking, and maybe still kind of are looking, for these things we call machos, which are just massive, massive objects. I don't remember, halo objects. They love to have acronyms.
Dude, the acronyms are off the chain with these guys.
Everything. They're just heavy things that we can't see for some reason. That's what a macho is. A macho is like a planet that doesn't have a star. Like a planet that doesn't have a star would have mass but wouldn't glow.
Interesting.
Nachos. Or a dead star, or just gas and dust that we don't see for some reasons. Black holes.
What's a dead star look like, you think? Have you ever?
Massive compact, Clive says it, massive compact halo objects are the machos.
Dude, your boy, massive compact halo object, dude.
Yeah. And the glorious thing is that the main competitor to machos is WIMPs.
Right, naturally.
The opposite of machos is WIMPs. WIMPs are weakly interacting massive particles. And what that would be is a macho is like, it's a black hole. A WIMP is, it's a subatomic particle.
It's a subatomic particle hole.
Yeah. And so we have modify Newton's dynamics, machos, and WIMPs are kind of some of the three of the big headliners. And then there's another one that's, no, your measurements are just wrong.
Yeah.
And so they're all out there, and they're still trying to research. And the way it goes is they'll say, like, for example, let's take the machos. They'll say, okay, I think this is black holes. And then they'll look for a prediction that is made by that hypothesis. You'll say, I hypothesize space is full of black holes and we just can't see them. And then they would say, okay, if there were black holes of that size and that number that you need to account for this, how could we observe that? And they would say, there's this observation that you can make if that's true. And then they go and they look for that observation and they eliminate. They have eliminated the large black holes through that process. And they say, okay, so much for that theory. It's not that. It could still be, there's a small band. There's like super small black holes. No. Super big black holes, no. I think if I remember right, it's like a middle zone that it could maybe still be.
Right, like an average size black hole.
No, the average ones have been eliminated. It's not the average ones.
Oh, so less than average?
Yeah, I think if I remember right, maybe somebody knows better than me where we're at with machos right now. Most of the WIMPs have been eliminated too.
Dude, I'm holding out for the WIMPs, man. I like an underdog story.
Yeah, me too. Actually, I'm on Team WIMP myself. I think it's probably WIMP. Although there is Sabina Hofstetter. You may watch her. She's pretty good.
Dude, I actually don't, and I don't think she's very cool. But I did watch her recently for something. Yeah,
okay.
she just doesn't.
Like more.
Yeah,
because she does speak the skeptic language quite a bit.
Nah, yeah, she dropped some gravy on LIGO that I was interested in, but I've seen her speak on some other things, and I was like, all right, well, I'm never listening to you again.
All right, yeah. Well, she did something that I.
She seems nice though. Shout out to Sabrina, dude.
Which is that there's a logical fallacy here that we're falling into, which is that there is only one explanation. Like, some people think it's the modified gravity equation. Some people think it's the macho. People think it's the WIMPs. How do we know it's not all three? We don't know that, right? It could be, and it's kind of looks like it's more than one of those playing into it together, causing us to get very confused when we look at the data. Because some of the data, you look at it and you say, this cannot be this theory. And other of the data, you look at it and that cannot be that theory. So what is it? And right. And so the possibility is maybe it's both. Maybe cool. It's, a little bit of both of them.
Yeah.
But we don't know. Right. So that's the reality of science. That's how science at its best. Right? That's not a criticism of science. That's praise of science.
That's how it functions, right? Because they say that science doesn't actually prove anything. It just proves like what it's not or something like that. I forget the way it's worded, but yeah, it totally falls in line with what you're saying, though.
Yeah, we eliminate the impossible, right? We keep eliminating the impossibles until whatever we're left with is like this is the best we have.
Super likely, right? Yeah, well, I'm glad that you understand that, because there's a lot of people that think that science, hands down proves something unquestionable, it's settled, and you're retarded, and So that's
not empirical science. Empirical science is always subject to some errors and unknowns, right? Yeah. Stuff that we had no idea about before will eventually be discovered and will completely change the way we think about everything.
For sure. I 100% agree. There was one more thing. So in the email thing, when we were talking about black holes and that guy's critiques on them, there was one question I don't think you answered on it, and it was Newton's equations are within Einstein's equations, right? But in Newtonian gravity, singularities aren't physical objects. Oh, that's right, because you said I couldn't find anyone. No. I have a bunch of quotes. He goes on to quote like a bunch of physicists and stuff that are saying that they're physical objects and stuff. That's what he was talking about in terms of that, because we were like, what do you mean by physically?
You can cherry pick the quote mine, but
it's not. I don't think that that's necessarily the case, because they're presented as physical objects that are pulling in matter and sucking them in, right? But in Newtonian mechanics, they're not doing that. Right, because it's understood as it's math. It's just a mathematical artifice, they call it.
No, that's not accurate.
So is there black holes in Newtonian mechanics then? Or?
Actually, yes. There were, and there still are. Well, the thing though is, it depends, right? Newton thought, we're doing a history lesson now, right?
It is, sure. I'm just
Okay. Newton thought that light were particles.
Right.
Was made of like some kind of
like cheddar cheese and shit.
Right.
Dude, how crazy would it be if the sun was a big block of cheese and it was sending cheese rays to us?
Yeah, that's cheese rays. I'm down with that.
That's my new theory, dude.
Stokes the cheese rays. So, yeah, I mean, Newton thought that light was made of particles. He rejected the idea that light was a wave. And as particles, he theorized that we had measured the speed of these particles already. He had measured that. They had measured that. And he knew that it had a speed. It was very fast. So if gravity got so large, the light would orbit. These particles would orbit around an object, and if you got even larger, that orbit would decay and crash, right? So yeah, the idea of the dark star is what it was called. I forgot the name of.
Okay, fair enough. I see what you're saying. Gotcha.
It was a scientist, not Newton himself, who coined the term dark star. And he did the math on how massive a star would have to be to suck in light. John Mitchell. Thank you, Clive Wells. That is correct. Yeah. And then Laplace came up with the same idea. So yeah, under Newtonian dynamics, I guess you would still have that. Only it turns out that light is not a particle like that.
Okay, yeah, I guess he was completely wrong then, because what he was saying, that it was completely different, and he provided there's a whole ton of quotes. Like it wasn't just like 2 or something. He's got like 7 or 8 of them, that seem pretty consistent. So anyway, what you're saying,
the fact of it is, in Einstein's equations, there are singularities, or we can get a singularity. Singularity just means like a spot where the math doesn't work. Really is what it means. It's like if you put the math in here, it explodes.
When it goes below your boy Schwarzschild, his radius or whatever, that's when it collapses in on itself or whatever, when it breaks apart at that radius.
Yeah, and it's at the very center that you get the full singularity.
Word.
You could transform your way around the singularity at the Schwarzschild radius, if I recall correctly. It's just the singularity at the very center. It's a divide by 0. It's going to explode.
Dude, I was always told you're not allowed to divide by 0.
Exactly, you're not allowed to divide by 0, which is why it's going to explode. And so the question then becomes, what is that? What does that mean? What is the math trying to tell us? In my opinion, the correct way to interpret that when you encounter that is to say, what is the math trying to tell us about this? Usually when you get that, like in an equation, you get an answer that's ridiculous, that is impossible, right? An impossible equation. It's telling you that that's a physical situation that's not possible.
Right. So real quick, why aren't you supposed to divide by 0, like normally under normal conditions? And why is it acceptable for them to do it in GR?
The answer is undefined. I mean, if you're just doing like take 100. 100 divided by 100 is 1, right? 100 divided by 50 is 2. 100 divided by 10 is 10, right? As the numbers get smaller, the answer gets bigger, right? 100 divided by 1 is 100. 100 divided by 0.1 is 1,000. It keeps going bigger and bigger and bigger.
Right.
So and here's the math language. In the limit, as the divisor goes towards 0, the answer goes towards infinity. Right? So one answer is dividing by 0 gives you infinity, except there's a even worse snag. If you think about it now, what about -1? 100 divided by -1 is -100. Right? 100 divided by negative small number is negative infinity. So.
Oh yeah, the old negative infinity.
Yes. Right. So if you really look at what does it mean to divide by 0, it means the answer could be infinity, or the answer could be negative infinity, depending on which way you were coming at the curve.
Right. Okay. Yeah. So let me ask you this.
We just say undefined. That's the math telling you that's not possible.
So under normal circumstances, right, you wouldn't do that. But why do they do it in GR?
Well, they don't. Well, they don't.
I thought you just said that it was when you divide by 0, you get the infinities
Well,
in
it's
GR.
another thing. It's a singularity like that. It's in the equation. The equation has like what happens when you go to the very center of a black hole. The math says at the very center of the black hole, you get a singularity. You get one of these impossible answers. So we don't know. Does it go to infinity? Does it go to infinite density? That's what you kept saying. All it means is infinite density.
Yeah.
We don't know that. Nobody can go in there and actually look and see and say, oh, yeah, sure enough, I measured the density. It's infinity. That's not something we can do. That's what the math shows, right? And so then the honest question is not, is that a physical reality? No, no. We don't know that it is.
Well, no, the math shows that. So it would be fair to say that it is claimed by the math that there would be an area of infinite volume and density and all that, right?
I would say the better answer is the math breaks down at that point. Our mathematical model, GR, probably doesn't work anymore there.
That's a fair enough way of putting it, because I've heard it presented as whatever it was I just said.
I mean, we really don't know. Maybe the GR is that. Maybe it really does go to infinity.
Sure.
Maybe. I don't know. Maybe there's another force, a fundamental force of nature that we don't know about that prevents the matter from getting more compact than that. And at that point, it's not matter anymore. That's one of the things that's really confusing about black holes is what do you mean when you say matter? We usually mean protons, neutrons, electrons, right? Mm-hmm. We mean atoms. Well, the atoms were gone when it was a neutron star. There were no atoms. It was just neutrons. And we're like, okay, we get neutrons are still matter, right? And then once it's not a neutron star anymore, what is it? It's energy of some kind. And we honestly don't know. At that densities, nothing in our laboratories can simulate that.
Do neutrons attract to each other, or do they repel?
They
one another
because they will repel if they're not going to attract. There's a funky force going on in there.
Yeah, I once heard it argued that that the collapsing, the so-called collapsing of a star, couldn't happen because what was it? It was something to do with how the neutrons repel each other, and there wouldn't be enough force to overcome that, and it would never happen.
Yeah, the neutrons are going to very much try to repel each other. Gravity is what holds it together. So,
yeah, but a lot of stuff easily overcomes gravity. So
not if you have enough of it, right? This is just basics, right? Enough pennies outweighs $1. Right? That's just right. 100 pennies is equal to $1. 110 pennies is more than $1. Done. All right. So we know the neutron force is stronger than gravity. Yeah, but gravity keeps building up. Keeps building up. If you build it up to a certain
point, so does the repelling force, though. Yeah. Like how could it ever overcome that if it's also building that as well?
We have studied, right? We have studied how gravity works, and we have studied how neutrons work. And we take the equations that we've learned for how we model those. We take our models of how that seems to work and how that seems to work. You put it together and you ask the question, what happens when a star this large runs out of fuel? And you add up the forces and you say, okay, the forces of the neutrons are going to try to make the thing explode. The forces of gravity trying to make it pull together. You add them all up and see which is bigger. And at a certain size, the gravity wins.
But why would it? So I think the argument was, why would it? How could it get to that size before it outweighs the repelling force to begin with? I think I can't remember the full argument, but it sounded pretty solid. It was something along those lines that it, like, dude was like, it would never happen, and it was I think it was yeah, I don't remember who said it, but yeah.
Early on in this discoveries, there were many very reputable scientists, Einstein himself, who said that this is just a quirk of the math and it would never happen. But then, since then, we've learned more about the nuclear reactions that go on inside stars, and we've learned that, you know what? No, it could happen.
What do you mean by the nuclear? Like, what do you mean? Like, you've learned about what goes on inside of a star? Like, how have you determined? How is that determined?
Well, I mean, Einstein was around when we first split the atom, right? Right. That was the first atomic experiments were being done in the 30s and 40s. A lot has been learned since then, right? About how fusion reactions work. And, we were just getting started with quantum mechanics back then. A lot of more work has been done to learn more about those things since Einstein's day.
Okay.
Yeah. And it's just been like, at the time, we don't know. We never seen a black hole. It didn't seem likely that such a thing would be possible. The math said it could happen, but that doesn't mean it really happens. And that was Einstein's position himself, was just because the math says it could happen doesn't mean it really happens. So we got to find more. And yeah, we don't just look at the math and say, oh, the math says, therefore it's real. We don't do that.
Okay.
We look at the math and say, what is this math trying to tell us? Like your infinity, your singularity, what is the math trying to tell us? It could be telling us that the math is no good down here. Or it could be telling us that there's another force of nature that we have yet to discover. Or it could be telling us that, it honestly, some people even talk about, it could be telling us that a black hole in our universe is a white hole in another universe that's creating a whole new universe. That's what some people say. And, because you can interpret the math to mean that, right? That it's all going in there. It's got to go somewhere, so it pops out on the other side.
It's got to go somewhere, man. Yeah. All right.
Yeah, and it's basically just a fantasy, right? You don't know if that's true or not, and it could be. It's not real.
What do you think about that? What's your opinion of it? Are we in that black hole, white hole universe, or what's up? Are we a multiverse? What do you think, dude?
The most important thing I would say to answer to that is, it's not science to answer that. Science requires that we could test it.
Well, just for funsies. What do you think? What do you speculate on?
Funsies, though. Where is my bet at? I'm starting to kind of like the quantum mechanics multiverse a little bit. But that's a different kind of multiverse than what you're talking about.
What kind of multiverse are they fucking with over there in the quantum?
Well, the quantum mechanics multiverse is every quantum mechanical collapse that occurs is, things can be in superposition. They can be both. The Schrodinger's cat is both alive and dead, right?
Heard of that.
Okay. The multiverse explanation says, yes, Schrodinger's cat is both alive and dead. There's one universe in which he's alive and one universe in which he's dead. And then when you open the box, you will find yourself entangled with the universe, one of the other of those universes. You will find that either in your universe, the cat is alive, or you will find that he is dead. But actually, both of those are true. You have, in one universe, you have found the alive cat, and in another universe, you have found the dead cat.
And your money's on that one?
No, I'm starting to kind of like it because it makes more sense than it sounds like. Because when you describe it, it's like,
yeah, when you described it, that sounded legit like some of the craziest stuff I've ever heard.
yeah, it sounds absolutely crazy. But then if you actually dig into what the math is trying to tell you, that's what the math is trying to tell you. That's what the math says.
Dude, if the math ever told me that a cat's alive and dead at the same time, like I'd be like, "What the fuck are you talking about, math?"
Oh well, that's old news, right? That we've known that.
It's the old math. Is that the old math?
Yeah. The fact that the cat is, I mean, really, it doesn't work for cats. But
I'm just fucking around, dude. I got you.
Yeah, no, the fact that the quantum cat is both alive and dead is just a known fact at this point. We know that.
I'm naming my next cat. Quantum Kitty.
Quantum Kitty. Yeah.
Okay, so real quick about quantum mechanics and black holes. Are you familiar with the information paradox and Hawking radiation? What are your thoughts? What are your thoughts on that?
Vaguely, yeah. What are my thoughts? I think that it's an interesting question. Do black holes destroy information, and does that violate the sanctity of information in quantum mechanics? I don't know enough quantum mechanics to really say for sure that the information being destroyed here is sacrosanct, that we can't just destroy information. I'm not enough into it to really understand why you absolutely cannot. But
yeah, I'm not sure either, to be honest. But quick plug, real quick.
Yeah, go plug.
I do have a debate uploaded. It's like a friendly debate between 3 astrophysicists and like a theoretical physicist or whatever. You know, and what's the other one? Astrophysicist, astronomer. I don't know. Anyway, they're all, you know, the people that are qualified to talk about that, and they're having like a friendly chat about it, and they discuss like the paradox and stuff. And it does appear to be a significant deal. You know, that they don't really have an answer for. But yeah, if you guys want to check out that debate, it was pretty interesting, you know. And like I remember I watched that back when I believed in all that stuff, and it was super interesting. So, but now it just seems like it kind of invalidates certain fields of study. But it's very cool though, if you guys want to check that out.
Yep, it's interesting. I think it points to, more than anything else, it points to unknowns that are yet to be learned. Right.
Yeah, fair enough.
We know we're always learning more. And so when you discover something that looks like a paradox, then it's time to learn something. Right.
Well, they discovered it 50 years ago. You think they're going to learn? You think they learned anything yet? Like, how long do you think it takes to learn?
Yeah.
Just some of it
has been disappointingly slow. That's true. Yeah. But, you know, we got quantum computers now, so that's happening.
Yeah, hopefully those kick in. So if quantum mechanics is real, then black holes can't be real then, right?
That's not true.
Well, if
that's a weird thing to say.
Well, black holes would invalidate quantum mechanics if they were detected by Hawking radiation, right? Because that's the whole information paradox.
Well, no, the information paradox, it suggests that under quantum mechanics, information cannot be destroyed, but that black holes seem to destroy information. What means is that one or the other of those two statements was not true.
Well, right? What they say is that I forget what they call them, but these particles that spawn into existence and then collide with an antiparticle of itself could hypothetically spawn into existence next to an event horizon, and the physical particle would be, or no, I'm sorry, the antiparticle would be, no, I can't remember. One of the two particles wouldn't be able to collide into the other one to, you know, disappear, whatever it's supposed to do, and the other one would be ejected away in the form of radiation. And like, you know, in that debate, that like they're hardcore, like, you know, that pretty much ruins, like they're pretty adamant about it, you know.
Yeah, no, it's a big deal. But what that means is not that black holes don't exist, because we now know they absolutely do.
Well, you guys have like a picture of an alleged accretion disk, and then the LIGO gravity waves are there was like 2 waves detected, right? And the one was super weak, and I believe it may have been even outside of the air tolerance or whatever for that detection, but they kept it anyway. And then the second one was detected while they were booting up the system before they had the filters in place that would eliminate like background noise and things like that would stop false positives from being generated. Well, they claimed that they detected it during a test run boot up, and those things weren't even in place. So like, there's no way to even know, like, from the official narrative, this isn't even conspiracy stuff.
Go to Wikipedia
Uh-huh.
and look for the list of gravitational wave observations from LIGO.
I'll send you the papers on all of them. I've got.
Okay, before you go to the papers, that somebody told you there's only 2.
Those are just two in reference that are propped up, dude.
There's 2 a year minimum.
There's like a history of it that goes on. So, and I think even they were saying that they couldn't isolate. Like if an airplane flew overhead, like it would fuck with it. If there was any seismic activity, it would fuck with it. And I think both the stations are built on fault lines. Like there's a lot to be desired with it.
But that's why they're on opposite sides of the country, right? So if there's like a truck drives by and shakes one of them, it doesn't shake the other one at the same exact moment.
Yeah, but if you were presenting detections of stuff, like, and then you present a quote unquote confirmed detection before you even had the things on that would eliminate that background noise, like that's. Like from where I'm coming from my perspective, like it just seems like they're grasping at straws, dude.
Yeah, well, you're coming from a skeptical position, which is okay. I mean, I understand.
Well, let me get one more point across.
But just, it's more than 2. It's a whole bunch of them, and all these things you're just like splatting at it. Yes, they've thought of that, right? Go and look at their answer for how they thought of that before you just sort of accept that they didn't think of it.
Fair enough. It seems like they did think of it, but just they don't care because they need to present this stuff to justify their money spent on it.
Think of it, and that's why there's 2. There's 2. So if there's a seismic event, it would be different.
It doesn't matter if there's 2 if they're going to present something when they didn't even have the filters in place that eliminates background noise.
If that's the
don't give a shit, bro.
If that's the only detection,
I'll give you another example.
A legitimate argument, but because there's a whole list of detections since then, why are you even bringing that up?
Are you familiar with how CAPTCHAs used to work, like the history of CAPTCHAs?
Yeah.
Basically, when Google would drive around and with the streetcar thing and getting camera stuff or whatever, they would have low quality images of people's addresses and stuff, right? And they used those as CAPTCHAs, and we trained, the algorithms on how to identify what those CAPTCHAs are. Because what they would do was they created a system where if everyone agreed that like this number was a 6 and this number was a 3 and so on and so forth, if a certain amount of people agreed to it, that's what the answer would be, and that's how they can train the algorithm, right? Mm-hmm. So if you don't have anything to train the algorithm on, then what you're presenting. So hold on a second. So what they've done with these gravitational waves that they're detecting, they've come up with their own things that like how the gravitational waves should look. They've come up with their own data sets. They've never observed a gravitational wave, like, right? They've made up their own thing.
What?
So
no.
If you're listen. No. Just let me finish this. So if you're trying to detect a gravity wave, right?
Okay.
You would first have to observe a gravity wave, right? And then like dissect what it is, right?
No, that's not.
You would first have to detect something happening, and then figure it out, right?
Right. The LIGOs do.
But you would have no idea what it is you're detecting, right?
No, see, you're portraying a view of how science should work, I think, that is just way wrong. let me say back to you what I think you're saying. Before you can invent a detector, you have to first observe the thing that you're going to try to detect. Is that what you're trying to say?
Not necessarily, but okay, yes. In the terms of like natural science, yeah, that would be right. Because you have your natural phenomenon that you're observing.
That's just a science contrarian thing. That's not how science works.
Science doesn't work with observation, experiment, hypothesis, and controlled variables and all that? Because if science doesn't work like that, then you could easily just make a data set and say that, oh, look, you detected the thing you thought you were looking for.
No, science does not work like a grade school textbook probably taught you that it works. Yeah, that was a very cursory children's view of how science works. The real way that science works is you do have the hypothesis, right? You make a prediction based on the hypothesis. You design a test.
What are you hypothesizing about?
Doesn't matter. Doesn't matter where your hypothesis comes from.
So you don't need to observe any phenomenon or have any basement or you can just make some shit up and then test for it. I don't understand.
No, and if you look, guess what? I have a video on that too in my channel. If you just do a cursory look for what is the scientific method, what is the scientific method, you'll find dozens of different answers. Because there is not one scientific recipe. It's not an incantation that we say like a spell.
Dude, yeah, Wingardium Leviosa, bro.
It's not Wingardium Leviosa. It is, and the reason that you find those different explanations of it is because that's to teach kids what science is about. And the observation part.
Why would you teach them what it's about?
That we're focusing on here is the story that we tell of the science that we're doing, right? When we talk about Newton and gravity, the apple is a story. It's not part of the scientific method. The apple is not required. Okay.
The observation is things fall to the ground. I'm not talking about a narrative attributed to the discovery or whatever.
About
an observation, bro. Like, what are you talking about?
Do it. About half of the scientific methods that you're going to find do not mention the observation. It is not a requirement. And I'll take you even further and say, why is it not a requirement? Logically, let's just do logic here. I saw Bev in the channel earlier. Is logic. Logic. If I have never observed ever before any phenomenon that that matches gravity, does that mean weight is not real?
How would you even postulate that it's real if you had no reference or seen it in action or had a thing to compare it to?
That's the thing. Why does that matter? It doesn't. It doesn't invalidate the experiment that I did, right? If I do an experiment,
the experiment you did about weight would be based on things falling down and having weight. Like,
I made a spring and I put things on the spring and I see, oh, look at this. The spring compresses when I put things on the spring. Based on that experiment that I just did, I can now draw a law. I can draw out an equation of all the different things that I put on that describes the weight of objects in terms of the squishiness of the spring. And then if you're going to come along and say, why did you do that experiment? What natural world observation did you have? Does your objection mean that all these measurements that I took of the squishiness of the spring aren't real? I measured a squishy spring. You can't undo that just by saying.
Witnessing. Hold on a second, bro. Let me interject here. So you're pressing the spring down is your observation. Trying to figure out why would be your hypothesis. Removing variables and trying to figure it out would be the experiment. Like, I don't know what
I woke
I
up
don't know
one
what you're
morning.
talking about, bro.
I woke up one morning and I dreamt that bigger rocks would squish a spring more than smaller rocks. So I said, I wonder if they really do. I'm just going to get a spring and I'm going to get some different rocks and see if big rocks squish the spring.
If you've never seen a spring or a rock, how would you ever conceptualize those in your mind?
I had a dream.
Your dream would be coming, allegedly from your subconscious or something. So you would have to have seen those before anyway. So
that's my observation. That's my observation. Right. I had a dream.
Your observation is the thing you're doing, though. Like, that's not.
You're just trying to come up with an excuse to throw out valid science, and your excuse is it has to come from an observation. No, it does not have to come from an observation. Nobody cares what gave you the idea to do this experiment. Once you've collected the data is real.
Do you think that you would have an idea to do an experiment of something or hypothesize about it if you've never seen it before? Like, that's like,
I don't know. I don't know, because the real reason they do these experiments is because they saw something in the math. They looked at the math, and the math said, hey, look what would happen if this math is correct. That's my observation. My observation was in the math. You guys just don't like it.
No, you just pulled a reference of something and then used other things that you're aware of to make an experiment. That's not the same thing as what you said earlier with the spring thing.
Yeah, I'm making up all kinds of stuff. Because the point is that the observation that you're trying to trip us on is
I'm not trying to trip you. It just makes sense.
It's not a requirement of the scientific method, and the people who are insisting that it is are only doing so for the express purpose of trying to deny science they don't like.
I think that the express purpose of it is trying to avoid people coming up with fake science and then saying, well, the math explains it, so therefore, X, Y, Z.
Why is that? Any testable observation that you can make is real science. There's no such thing as like fake science.
Testable observation you make.
Yeah, if you can test it, it's science. Right?
Right.
We've mostly agreed on that ever since Karl Popper. We've agreed if you can test it, you can falsify it or test it in some way, it is science. If you cannot, it is not science. Right? That is the scientific method. That's the real scientific method.
So reiterate again real quick. What's the real scientific method? If
you can test it for falsification, it is science.
And okay.
It doesn't matter where you got the idea. If you got the idea from the math, great. If you got the idea from a textbook, wonderful. If you got the idea from something you saw in the sky, cool. Once you've made some kind of prediction that you can test, you do the test, that is science.
Now, if your test is just more observations, what do you think about that?
What's wrong with that?
You're not able to manipulate any variables.
Tests is always more observations, right?
But without changing any variables, just looking at shit.
Well, see, that's where
you just assume. No, because then you just assume because then your presuppositions you assume are correct, and you can just move forward without actually having to do anything else. And then when you run into things like a galaxy spinning too fast, you're just like, well, whatever, just add more mass. Like, that's why it's like that, because you have this conceptualized idea.
That's not.
You have this conception. conceptualized idea that natural science is invalid. We're looking at it through looking at natural phenomenon and then figuring out those things like.
No. I did not say natural science is invalid. What I said was you trying to hold the world of science to some kind of rigid set of rules that they do not hold to is not valid. You don't get to define what is and what is not science.
Do we live in nature?
Do we live in nature? Define nature, first of all.
Let's see. The place you exist, right? So when you look out and you see water and trees and stuff in the sky, and you see a sky and clouds, nature, yeah? Okay. The place where you live, right?
Well,
so there's
the reason I ask is because the usual argument here is that man-made objects are not nature. And I would say that in science, no, that's not.
No, that's what I'm talking about. I'm talking about naturally occurring phenomenon, right?
Okay. Yes.
Phenomena or whatever. Okay. Yeah. So you it seems like you're super against that, testing things against that criteria.
No, I'm not.
Okay.
But LIGO is observing in nature.
How's that?
My observations of, somebody's going to observe a distant quasar. Those are observations of nature.
Looking at a light in the sky is observing something in nature. Agree.
Yes.
And then to further hypothesize that there's invisible, gravitational waves that are traveling from this thing, and then that's going to interact with you. And then you've never seen that, right? So you got to extrapolate a way to predict what that would look like, right?
That's correct.
It's not science.
No, it is.
No, it's not, because you could just cook the books and it would be whatever you say it is, bro.
No, I didn't.
No.
Hold on.
Sorry.
You are making a very specific claim about how you made it not science, and that is to cook the books. Cooking the books is not science. I'll agree to that. You could just cook the books. Right. Sure, you could just cook the books.
So if you came up with a predictive data set and you didn't find any matches, and you continually changed that data set and altered it until you did find a quote unquote match for detection, would that be science? No, because you can't compare it to anything natural, right? So that's just made up stuff.
I don't know what you're going on about. You hold on now. You have a data set.
Yes, the LIGO
data set, you make a prediction.
No, LIGOs, the way that they detect things with LIGO, right? They've come up with a bunch of data sets of what they think a gravitational wave would look like.
Okay.
Right.
And so then they built a device to specifically look for that signature.
And they have nothing to compare it against, right? And when they couldn't find anything, hold on a sec.
Nothing to compare it against. What does that mean?
Okay. There's no gravitational. Nobody's ever observed the gravitational wave affecting anything.
Right.
In the way that they just. Right, and it's made from a data set that they've constructed and altered when they couldn't find anything, and have made changes to it so that they can find things. Yeah, they have.
No, that's just not fair. That's not
okay.
Fair
Well, how so? That's cooking the books, brother.
That's not what they did.
That's a book cooking operation.
That's not how it works.
Okay, well, I'll send you the papers.
And that's not how it works. How it works is they looked at the math. Math made a prediction. The math said there should be gravitational waves. And then a lot of people sat around and said, how could we possibly detect those gravitational waves? And they built this device specifically for the purpose of doing that. And they said, what would the gravitational waves look like under certain conditions if they existed? That's what we're looking for. So that's the prediction. You make a prediction, and then you do an observation.
A massive data set that you've created that could fit different possibilities, dude. Like,
no.
Yeah.
No.
Oh, dude. No. Oh, dude, do you think that they just made one prediction?
No.
Like,
The prediction
what are you
is there
talking
will
about,
be a
brother?
wave, and the wave will have a
No.
signature
Uh,
such
uh,
as these. It's
are you
not
saying
just,
that the? Yeah. So you're saying that the such as is just one thing then? Because they created You don't know that they created multiple data sets and they've altered them and shit.
the fact that you think that that's bogus is what's really tripping me up.
The
You're
fact that
not
you
going
think
to
it's
get
really
just,
legit is what's tripping me out, bro. Like, that's crazy, dog.
is he calling the LIGO scientists liars? Yes, I think you are, right? You are calling the LIGO scientists liars.
They believe what they're doing.
They
Just
believe
like
it
you
is.
believe,
Okay.
just like you believe it's real science.
And
It's not.
the fact that you don't, okay,
No,
when I'm looking for the signature on a radar gun of a speeding car, the first person to make that got the first detection ever of it, right? And the signal he was looking for was calculated by the math.
I don't
We're
know.
cool with that. But now all of a sudden we're not cool with it on gravitational waves.
To
Right? That's how we do, right? That's
Yeah.
how you do. You just say, I'm looking for something like this. I specifically design an equipment to look for that. And then when it comes in, I test it against what I was looking for.
Totally.
And if you get that, that's confirmation that what you were looking for, it was real.
Okay. Can you post the link that I posted, please, for that? I want to show that guy something that said something about everyone being a liar at LIGO, because this should help illustrate why that's not true at all, and nobody claims that I'm aware of.
Okay.
So the theme,
yeah, that one.
Yeah. So
yeah,
a small team was given access to their facilities and stuff, and they implanted a system where they could simulate a gravitational wave detection, and they did it under the guise of it being for legitimate purposes and blah blah blah. And they ran their simulations without the scientists knowing that actually worked there and stuff, without their knowing that that was going on. They thought they detected a gravitational wave. They worked on it a whole bunch and tried to debunk it and stuff, and did all their proper science stuff to it. And they were about to go to a press conference and release that they had detected it, when they were informed by their department head that it was all a ruse and blah blah blah. Right. So those people aren't you don't have to be in on it. They believe it. It's just not real.
Has to be in on it though. And I would also say that if they had not come out,
so few people would have to be in on it.
Somebody would have eventually caught them.
Is that what you think?
I think that, yeah. Having worked in places like that.
Has anyone ever has anyone ever disclosed what exactly goes on in secret military bases, Area 51, or the ones that we don't even know about? No one's talking about those, so that's not true. Shit can be hella compartmentalized. Okay. People can no. People can do things under the guise of like for example, the team that implanted that the LIGO stuff and changed their systems, right? They could have been doing that under a completely different guys, thinking that they're doing it for legitimate reasons, this is going to help them test and blah blah blah, and this will help them scrutinize it better.
You breezed over a logical fallacy there that I just gotta call out.
Go ahead.
Which was because we haven't caught them, that proves that they're really good liars.
What?
All this Area 51 stuff, nobody knows about that.
No, your point was
we don't know about it because there's nothing to know.
No,
your point was an assumption that there is secrets that you don't know.
There's military operations that happen that nobody knows about, dog. Hold
on. No, seriously, the logic of what you just said. Nobody knows about it, but it exists. How is that possible?
I understand what you're saying, but is it really your position that you think that things have gone down that you don't know about and that have never come to light that were really bad?
I assume that there are things that have never been discovered. I cannot prove that because that would be a logical fallacy, right?
Okay, well, I assume that then whatever I said, just assume to it. And
Yeah, so you're making assumptions about how this stuff works.
Okay, so then I assume it, but then your claim would be that it would have to come out, right? That's your positive claim, that it would have to come out. But that's not always the case.
That would most likely come out, yeah.
There's unsolved murders. There's all kinds of shit happens where people don't know what happened or what went down. Secrets get kept.
Everything that has come out has come out. There isn't a single thing that has ever come out that did not come out. Right?
Has anyone ever gotten away with a murder?
Of course.
Okay.
Yeah, there are unsolved mysteries. You're trying to say, are there no unsolved mysteries? There are.
So secrets were kept, right?
Okay, yeah. I can give you that. There are definitely cases where secrets have gone kept.
So under highly specified conditions, i.e., military compartmentalization, security clearances, people being vetted, that are the least likely people to snitch, so to speak. So yeah. I don't think
you're a conspiracy guy, and we all know that, right? It's cool.
It has nothing to do with it. Conspiracies exist. People conspire against people all the time. If your wife plans a surprise birthday party for you, she conspired against you with the people to have a party with, So
well said.
Saying that I'm a conspiracy theorist isn't.
Well, no, I mean I'm highlighting our differences on this. Is you're saying that there could be a conspiracy, that LIGO is all being faked. And as evidence for that conspiracy, you're putting forth the time they admitted that they faked it.
I'm putting forth that the amount of people that would have to be quote unquote in on it is extremely low. That's all.
It's much smaller. You're saying it's much smaller than most of us think.
Much smaller than you guys think, and the idea that that everyone's in on it, is a fallacy, because I don't know anyone that's ever said that everyone at NASA is in on it.
Okay,
so that's all I wanted to point out with that, because a lot of people always hammer that. They're like, well, wouldn't everyone be? No, obviously not. If everyone was in on it, then everyone would fucking know. So the fewer the better.
We've talked about this before. My point remains the same, which is you have a very good point with that article in particular, that if a handful of people wanted to fake the LIGO detections, they could get away with it. I will agree. Yeah, a handful of people could fake LIGO detections. But my point remains the same, which is that you scale that out to all the stuff, and it's just out of control. It gets out of control really fast. It comes down to the guy that installs the dish on your satellite dish, for your satellite cable, right? He's in on it.
How's that? We just extrapolated that it doesn't have to be that way.
It does, because
how so?
The satellite dish has to be pointed at a very particular spot in the sky.
Okay, so if the LIGO team that installed that and did that to those other people, if this article never came to light and dude never said anything, nobody would ever know, dude. They would all believe that they did it. The only people that would know would be the people that installed it. And if you got them to install it,
understand that article says that they did it on purpose, on the up and up. This was not an attempt to fake anything.
That's what they tell you. But listen,
why would they admit it if that's not true? Why didn't they just keep it on the down low? If it's all secret, why didn't they just keep it secret?
Don't restrict it to just this particular instance. Just like in general, right? Not everyone would have to be in on it. There would be instances where they don't tell the people. There would be instances where you get people to install the thing under false pretenses. And then they wouldn't realize, they would never know that further detections were being used in that way. They would never think about it. They wouldn't like what would you do? Go ask your boss? Like you would get fucking fired, no, like you wouldn't
I would say that I have been close enough to that data that you couldn't fake it.
They did fake it though. Like, what do you mean?
Some kinds of data, not LIGO. I've never been anywhere near LIGO. Like space-related data. I've been close enough to space-related data that I can tell you that your characterization of how they can hide things from people doesn't scale to the all of space, right? I'm giving you, maybe they could fake LIGO, they could fake things like that.
What's your experience with space data then? Was this in reference to what you did for your undergrad? I think it was for the satellite stuff or satellite debris.
Yeah, it was in grad school. My best friend was tracking space junk. That was his job, was to track space junk. And so,
do you realize if that data was simulated and your friend was like adding to it and refining it, that he just would have created he would have helped refine the system that simulates all that shit?
I mean, you're portraying it completely upside down.
No, that's compartmentalization. That's how you would do it. That's exactly how you would. That's exactly how you would do it.
Upside down. He would have been creating data that would not match his own data set. What the heck are you talking about?
He was given data to analyze, right?
He was given data to analyze to improve the analysis of the data.
Right. So he improved the simulation system. I don't know how you don't see that. It could be possible anyway. Not saying he did. It could be real, but I'm saying the fact that you can't even acknowledge that is kind of...
No, it's just because you haven't done the work, you don't understand what the work involves.
How could the data not be faked? Explain to me how you could walk into court and go, this data from space is 100% irrefutable. There's no way that anyone could ever call this into question. What's your response? Because that data is not like that, brother.
It's really quite easy. As soon as the data has an error in it, and that has to be corrected, that is proof that the data was real. Right?
What?
You're predicting the orbit of a piece of space junk. And it turns out it's not where you predicted it to be. Why isn't it where you predicted it to be? Something about your model is wrong. You now have to do a complete study of why it was wrong and fix the model for something that was not predicted by anyone. And then when you make that prediction based on that, you look and see that was correct. Now we know why that happened. The only way that could be faked is if someone else has already planted the error into the data in the first place. When you are the research student who's inventing that calculation, how is that even possible? That someone else is ahead of you in the math that
what are we saying here? So your buddy gets data, right? From some source, right?
Huh?
Okay. He does an analysis of the data and makes predictions based on it.
Right.
And then he sends his findings back to the place where he got the data and they compare it against satellite debris, or what's up?
No, he just gets a new data set. He doesn't even send it back. You don't send it back for months. You don't send it back for months at a time.
Oh my God, bro. I don't know how you don't see it. Are you for real?
I don't really, I think the problem really is that you've not done work like this. So you don't really understand how it cannot be faked, because you are making a discovery, right? You're making a discovery.
Who's confirming your discovery? The people you're getting the data from? Who?
Peer review.
You can peer review space junk and confirm its location. How so?
Yeah.
What is he confirming? No. Listen. I swear I don't mean to be a dick about it. I'm genuinely trying to understand how it could be irrefutable data. Like what do you like? Because he's verifying where the debris is, right? That's what you were saying. So how can who's peer reviewing where space debris is? It's all coming from a centralized source, right?
It's coming from all over.
It all goes to
coming from a centralized source. No,
it all goes to the Deep Space Network, right? It's all filtered like through that system. I know a lot of stuff is. I'm not sure about space debris. What's that?
In 1996?
They use the deep space work now.
He's getting this stuff from radar stations all over the place.
Oh, sorry. Yeah. So
they're all in cahoots somehow. Okay, they're all in cahoots. Gotcha. Fine. They're faking the data that's coming to them.
They send all that data to a centralized spot, though.
No.
And then, yeah.
Well, he was a centralized spot. A grad student in Virginia is a centralized spot where we we've agreed to send all our fake data.
Yeah, could be. Like,
okay.
Yeah.
Okay.
So that he could then design a system that could.
So that he can then design a system
that nobody else that can
engineer the system we've already designed. Right.
So he could refine it and train it. Because it's like what I'm saying, that all this stuff comes out of like a simulation, right? So yeah, if he was working on that and then they send the data back, yeah, because all that stuff
comes out of a simulation. So someone's already built a simulation that's more advanced than what the grad student is doing.
It's advanced enough, and then your boy refines it.
It's feeding him better data than he's got. Right?
He's not making what, dog? Like, he's not making data. He's getting the data and then making predictions based on that. And then they're telling him that his predictions turned out to be correct, right?
No. They're sending more data. And then he compares against his models.
So how are you saying that it confirms whether there's a debris there or not? Who's confirming it then?
Yeah, what you're not hearing is that the model is going to be incorrect, right? The model will not be correct.
Back up a second here, because you said that his predictions and stuff would be, he was looking, he had a prediction for where the space junk would be, and then it was verified that there was no space junk there. Who's verifying the space junk?
What does that have to do with it? He's all.
What do you mean,
right?
Bro? What do you mean? Oh my God, bro!
Just listen for me.
I'm listening.
All he's seeing is the data, right? No one's going out and looking at space junk. He's got radar returns, right? Radar says there's a thing here. You're suggesting somebody faked it, right?
Yeah, the data is just gobbledygook.
Okay, data's just gobbledygook. So, using the best available simulation available today, we do a simulation on that data. And we
the data that your friend made
junk will be. And we predict where the space junk will be using the best available simulator.
Yeah, but using data based off the stuff that your friend would have refined, right? In this scenario.
We take the data we were given from last week. Last week's data. Using the best available simulation, we simulate it forward a week. And then we compare with this week's data. This week's data comes in. And we say, okay, it's off. It's not accurate. Why is it not accurate? And we need to dig into the best available simulator and find out why it's wrong and make it better.
So the new
make it better. And then we run it against the next week's data. When the next week comes in and see, oh yeah, look at that. We got it better, right? So we're doing a better job of simulating the fake data this week than we did last week, right?
Okay, who's incorrect in this scenario? The data that's coming in or the data that your friend made?
We're hypothesizing that the data is faked.
Right, but you're saying that when you go to check it against whatever, that your boy is wrong.
Every week the data's coming in of the radar junk.
So is it matching or one's wrong? You said one's wrong.
We're tracking the same 200 objects as they go around the sky, right?
Right.
And what we're doing is tracking the radar data we get versus our model.
Are your friends' predictions? Who? Man, goddamn! You said your friends. Because you don't realize what you're saying. I think, like, I'm not trying to be mean, but it's so backwards.
I did it, or I've sat next to the guy who did it, so I do understand it.
Well, how you're explaining it to me doesn't make any sense, because what you're saying, I'm trying to clarify what you're saying.
That's
You're saying
ultimately that's all that this is that I did it, you didn't do it.
That's
I don't understand how it works.
I'm sorry, I apologize. I'm just trying to figure out how the story is unfolding. So you said that he gets the data, right? He makes a prediction, right? And then he gets new data next week, right? Is his prediction matching the new data?
And it didn't. It did not match the new data.
Okay, so then what happened?
So then we need to ask, why does the prediction not match the data?
Mm-hmm. And what did your friend find?
We found errors. We found unaccounted for variables. And mostly
within your own work or the received data?
Within our work, not within the received data.
Okay.
Received
so when you can
ground truth fact as far as we're concerned.
Okay, I'll give you that. So your data wasn't matching what was coming in. You guys thought that an object would be here. The new data comes in, no object, right?
Right. And the object is somewhere else. It's off to the side a little bit of where it was predicted to be.
And then what happened?
From our working assumption, the data is ground truth fact. That means our simulation is incorrect and must be improved.
Mm-hmm.
So we find the mistake and fix it. And now it does much better than it did before we fixed the mistake.
Okay. And then your data starts accurately predicting along with the ground data.
And now it's more accurate. That's right. And so the only way this is possible, if they're faking it, now let's take the hypothesis, they're faking it. The only way that's possible is if they already know about the error that we find. And they're simulating fake data that has already corrected the error that we haven't found yet.
I see what you're saying. However, another possibility, right? Now hear me out. Okay. They've come up with a really elaborate, sophisticated system to generate this data of quote unquote space debris orbiting in space, right? Assuming it's all fake and there's nefarious shit going on, right? So they've got this data, right? They send it to you guys, right? You come up with calculations, like you're basically critiquing the system they have to see if there's like better possibilities without you knowing that you're involved in like critiquing a fake system. That's all I'm trying to say. And there's no
in that scenario, the error that we find can't exist.
It's within your own analysis, and then you fix it until it starts matching the real data. You're essentially reverse engineering what they've made.
You don't understand when I say we found an error. No, this is wrong. It's like, oh, why is this wrong? It's because you're not using the latest, just discovered techniques, right? Oh, let's try that technique.
You're talking about like mathematical analysis techniques?
Yeah, it's a mathematical analysis that you're doing, and you need to improve it. There's a mistake in it, or there's a substandard coroutine in here somewhere. You have literally improved it. The only way that would actually improve your tracking is if the people on the other side had already done that.
Okay, fair enough. Now what you're saying, dude,
edge, right? The cutting edge team, what you're suggesting, in order to compartmentalize this, the cutting edge teams, and this goes across all fields, the cutting edge teams are not the cutting edge teams. They are following along behind someone else who is the actual cutting edge team who's making up stuff.
Possibly.
And at that point, you now have two cutting edge teams for every cutting edge team.
Well, that's how compartmentalization works.
But those people don't exist.
To your knowledge.
Right. There must be hidden lizard people or something. I don't know where these people are.
It could just
but
be
nobody knows who
humans.
they are or where they are or what they're doing. But they exist, and they're so numerous that for every team you do know of,
there's a counter team.
A fake team.
Well, hear me out. In quantum field theory, for every particle, there's an antiparticle, bro. So I don't know, man.
We're right back to how many there has to be, and it's an astronomical number.
I don't think it would be that many, man. I think you could have people working on shit that are really smart. They build it. They build a piece of it. Some other team puts it together. I see what you're saying. Totally sound logic, but I'm saying there's ways around it that you can't acknowledge or won't.
It's a huge number, just massive, right? Just think about all the bugs, everything that ever goes wrong anywhere. Right. Then you guys find a bug? What you call the wheel, the momentum wheels that they put on spacecraft that seize up. Right. I mean, did somebody plan to have those seize up? Did they plan that scientists would study why they seize up? Did they plan that somebody would come up with the explanation of why they seize up? Right? I mean, no one knew that those wheels were going to seize up. And
what wheels are you talking about, bro?
What's that?
What are you talking about? What wheels? I'm sorry, what wheels are you talking about?
It doesn't matter what. Just a part on a spacecraft. A part on a spacecraft that a lot of spacecraft have.
And they don't. Who knows, man? I mean, I think that stuff's fake. So,
and when they don't last as long as they should, scientists do a study to figure out why, and eventually someone publishes, this is why that happens, and here's how to fix it. Right? So, this is a discovery. The moment of discovery. In order for that to be faked, you had to back it in all the way to the moment that they launched that thing in the first place.
You think people couldn't be working to solve a non-existent problem that would hypothetically exist if the thing did go to space and all that? Like, you don't think they would have like it's basically a big R&D project. You got smart ass people figuring out stupid shit like wheels on a spacecraft that doesn't go anywhere. No offense. And it's like your contention or your point is that because they have jobs looking into these things, therefore the thing itself must exist and be, it's very circular to me.
My point is that there's a cause and effect relationship here that has to be maintained, right? They eventually they discovered something about science no one knew before.
Yeah.
Right? That discovery is verifiable. It's verifiable now. It's true, but it was not known before.
Agree. We're saying the same thing.
Right. And it just so happens to correspond to a fake thing that somebody just happened to make up.
There could be a real problem, and then they have people trying to solve it. The problem doesn't have to exist within the confines of how it's presented to the people that are solving it, though. You understand?
It's a problem that only exists in space. It's a problem unique to space.
Right. So then they have people come up with stuff.
But space isn't real.
Correct. It doesn't have to be real for them to.
How can there be a problem unique to space, an undiscovered problem unique to space, if space isn't real?
It's hypothetical, dude.
It's not hypothetical. It's
real. And in the consistency of the lore, right? There would be problems, right? Now,
there would be problems, they are not yet known. They can only be discovered later.
Later, when they go to space, allegedly, right? That's your point. My point is, they don't go to space, dude, and they just.
How do they discover it?
You would never know if the solution they discovered works in space because they fake that shit, bro. That's why it's all CGI and shit, what they show us. Because they don't actually go anywhere. Like, some dudes probably figured out some shit.
Become a waste of breath a long time ago.
Okay, well, I apologize for that, man.
You think it could be compartmentalized and you think that probably there's a pretty large number of people who are in on it.
Negative.
Give me a number. Give me a ballpark.
I don't know.
How many people know the truth besides yourself? Right?
I don't know the whole truth, but
how many people at NASA know that the Earth is actually flat, for example?
I have no idea.
Less than 100, more than 100.
Okay, in terms of having actual access and being in on that need to know and really knowing for real, and not just like, oh, they figured it out or they assume it's all bullshit. Okay, if you're talking actually in on it and the people that are behind the scenes, probably less than 1,000 people.
Okay, I'm telling you that's not possible to fake the amount of data that you need with 1,000 people. And the fact that you think that it is possible.
How many people came up with the fake
LIGO
data?
Just tells me that you have no idea how any of this works.
How many people came up with the LIGO data that was used to be fake to trick them? Like they came up with it, bro. You guys come up with you guys
probably less than 6.
You guys come up with your own shit and then get tricked. Like it's not super hard to figure out. Sure.
Less than 6.
Yeah, it's not super hard to figure out.
Just for LIGO.
You don't, dude.
You didn't. Well, let's talk about GPS systems. Let's talk about satellite dishes. Let's talk about the weather prediction.
Fewer people than you would need. You would have people legitimately working on it to solve it.
Navigators and map makers and
pilots fly over a level plane. They're not in on it. No, it's not.
Thousands minimum.
Bro, you're wasting your breath saying that shit. And I don't mean to be rude to you because you're my boy, but now you're off and you're I think we should probably call it here, bro, before we get mad at each other.
It's super late. It's super late anyway. We obviously disagree about that. I keep saying though, you're accidentally, I don't think you mean to, but you're accidentally completely dissing half the planet, right? I mean, all engineers who work on this stuff, you're saying they don't know what they're doing. All scientists don't know what they're doing.
No, it's not what I'm saying.
Weathermen don't know how it works. Come on.
No, they're doing things that they think are in the confines of what they've been told.
Jezza agrees with you. I don't know about what, but yeah. They're doing things within the confines of what they're told. So yeah, the weathermen don't know how to predict the weather. Got it. They're just.
No, you're strawmanning me, bro. Bro, stop. You're tripping, bro.
Well, I mean that's what you're saying. I don't think you mean to be saying that, but that is what you're saying.
Right? I'm explicitly telling you that's not what I'm saying. And when you continue to say that's what I'm saying and adding more numbers to it, it's kind of pissing me off.
Okay.
So let's.
I'm sorry. Do you want
to? It's all good, man.
You want to tell me what you mean in your words? We could wrap up with that.
Oh yeah, I already did. Way less people than you would ever imagine, and you could just have people working on different aspects of the project that gets assembled by another team. Then the number of people that needed to be in on it, in fact, gets smaller and smaller, not larger.
Okay, and the weathermen that I mentioned, they were, they went to school, they learned how it works, and none of that was true. But they go to work every day and they do it.
What they're doing has nothing to do with the globe. It has nothing to do. It has nothing to do with space. It has nothing to do with that.
You think weathermen don't involve globes in space?
No.
Maybe you should be a weatherman at some point.
I'm going to. We already covered the NextRad system and the radar and the balloon satellite stuff. Yeah, there's no need for any of that to actually be in space on a globe. So no, like I feel like your inability to concede that is I don't know what to tell you, man. Like that's not what I'm saying. Like I that guy I was telling you about that I'm friends with that works at the that weather company. I don't know if I told you the whole thing, but yeah, he's got a radio. Like I'm gonna reach out to him and see if I can talk to a meteorologist about this stuff too. So that'll be forthcoming. But yeah, I'm not saying that everyone's a liar or that they're retarded or anything like that. I'm saying there's a great deception going on, and people are buying into it because it's hella convincing, and they've been told it's one way, and they see things on the TV, and they just go along to get along, and they get a paycheck for it, and they think it's real. They go to work every day, 9 to 5. They get a retirement fund. It's all paid for somehow, through our monetary system, and whether or not you know what all that's about,
Yeah, let's not get into it though. But yeah.
No. Yeah. So I'm just saying there's wiggle room in there to have massive R&D projects where you've just deceived people and you have them thinking that they're working on certain things and they're really not. That's all I'm trying to say, man. So.
Okay. That's excellent. Thank you. Thank you for the time. I will ask you for a favor.
Yeah.
I think you should go back to Jaren and Whitsitt and Darth with what you've learned.
Oh, I am. I took those notes. Those were some interesting things. Like I'm not here to pretend or whatever. Like I'm trying to find out my own shit. But yeah, I'm definitely going to run that stuff by them because no one's brought that up to them, like on stream or anything, or like no one says that in the comments. I've never seen anyone talk about what you said in any of the comments on the YouTube videos or anything like that. So these are new, these are baby fresh arguments, and that's what I'm here for, brother. To get that baby fresh shit so we can compare it to figure out what's going on so we know that we're on the right track. Because if we're fucking around on some stupid shit, then we're just wasting our time.
I agree with that. Absolutely. So yes, thank you for that. Thanks everybody. And we'll leave it at that. All right. Thanks for coming. We'll talk again soon. Good night, everybody.
Yeah. Thanks. See you guys. Thanks for having me on, man. Appreciate it.